But yeah. Okay, so we're good to go now. It's 5:13, so hopefully everybody's here that wants to be here. Let's see how many people are here. Do we need another streamer?
Not
45
yet.
people.
Pushing the limits, but not yet.
Yeah, but if they do need a stream, we do need another streamer. Just like tell me or tell someone that could stream, or someone just start streaming if they can. That would be nice too.
So what should the benchmark be once we have what, 48?
Well, once it's
Or
50, and then like when it, because there's no need less than 50. So when it's 50 people, then yeah, if someone could start streaming, that would be.
you don't count those, so you have to be 51 people in the servers. 51. Oh wait, 50 spectators. Okay, 50 spectators.
Yeah, I don't know if I count as a spectator when I have it open, but I don't think I count as a spectator.
Let's find out.
Yeah, I guess so. But yeah, when it's 50 people, that's when we need another person. But yeah, okay. So
You don't count, so it's
I don't count.
other than. I think so.
So we're gonna start today with just starting with the chapter 22 practice problems from PCS. We're gonna try to get through all of them: chapter 22, 23, 26, 28, and 29. So I don't know if we're gonna do all that today, but we're gonna just try our best to get through as many as we can. Chapter, I found the electricity web assign. So I'm trying to say the electricity web assign much harder than the magnetism one. So we'll see how this goes. I think magnetism I'll be able to do fine, but let's just see how it goes. I don't know how it's gonna go, but hopefully it goes well. Our first question is from chapter 22, which is this one. And just before I do that, you can find my notes, of course, as always, on my website, which is, I will put it in homework help. So you can go to www.tutor.
You must plug.
I must plug /notes, and there you can find my PCS notes, and you can follow along if you would like to, because I will be doing that.
Is there also merch on the website, or is that a different website?
I'll put merch soon. That's coming soon. No, it's okay.
So everything is here, and you have only these 4 classes, the ones that are like on the main page.
I have economics notes as well. I just didn't put them up there yet. They're not really complete in any way, so by Friday I will have economics notes there too.
Okay. And we're doing our economics study session soon.
On Friday.
Okay, thank you.
Friday. So before that session, I will have everything in my economics notes done.
I think.
Hopefully, if I get everything done, I will. I have to. So it'll be good. Okay, so let's start here. This is chapter 22, which is everything up to uniform electric field, like between 2 plates. So yeah, that's everything between those 2 sections. So it's like calculating the electric force, electric field, forces on 2 charges. Then there's also, that's it. Not even any kind of, no, because you don't talk about electric potential yet. That's true. Okay. So 2 small beads having positive charges Q1 equals 3Q and Q2 equals Q are fixed at opposite ends of a horizontal insulating rod of length D. Okay. Do we know what Q is? No, we don't. The bead with charge Q1 is at the origin. The bead with charge Q1 is at the origin, as shown in this figure. A third small charged bead is free to slide on the rod. At what point X is the third bead in equilibrium? Can the equilibrium be stable? So at what point is X at what point X is the third bead in equilibrium? So in other words, at what X value is the do we know any charges? No, I guess do we know that the electric field is equal in both directions at some point here on X. And in that case, then the force would be the same on the same object. So we don't know anything about the mass of the object. Yeah, so the forces are going to be the same when the electric field, the acceleration is 0 here. That's what that's going to be. So yeah.
So what do they mean by in equilibrium? Like equilibrium for like force, or like for V, like voltage, like potential?
Well, not potential, but I guess they mean like force. But remember, force is just QE, right? So we don't know anything about the. Oh, we do know the charge. Hold on. Yeah, we do know the charge.
No, we know it's Q and Q. We know that. We don't know a specific number.
We don't know a specific number. All we care about is just that this is 0. That the force is 0, which is either attained by, which is attained by the electric field being 0 at that point. Right? The electric field being 0 at that point. So at some point here, the net electric field is 0. And that is where the equilibrium point is. Does that make sense? So we got to figure out what's the general electric field for this value at any given point. Well, it'll have two forces acting on it, or two fields that add to it. So here, pointing in that direction and pointing in that direction, that's electric field 1 and electric field 2. So electric field 1, electric field 1 is, well, it is, so just a quick note here, the magnitude of the electric field is always Ke, Q, absolute value of Q, over R squared. So from this first one, well, okay, Ke, magnitude of the force causing, so we're doing Ke1, right? Magnitude of the charge that's causing the electric field, which is Q1, which is 3Q, right? So 3Q over R squared, which is X squared, right? And then the magnitude of the electric field 2 is going to be Ke Q, just Q, not 3Q, because the other one is just Q2 is just Q. And then over, well, what's the distance that it has here? Well, that's going to be d minus x squared. D minus x squared. Right? And we're looking for when do these two values equal each other? Yeah, when do they equal each other? So we're trying to figure out, I'm pretty sure, when does Ke 3Q over x squared equal Ke Q over d minus x squared? When does it equal each other? So solve for x. Well, we can cancel the Ke's and the Q's, and we're just left with 3 over x squared equals 1 over d minus x squared. Flip both fractions, so we just have x squared over 3 equals, and I'm going to FOIL this out a little bit, so d squared minus 2xd plus x squared, I mean. And then, well, the x squareds can cancel. Subtract x squared from both sides. Oh, no, sorry, they can't cancel. We can multiply, so this is x squared over 3, sorry. So I'm just going to, I guess I'll just do it. So 0 equals d squared minus 2xd plus x squared times 1 minus a third, which is 2 thirds. So I'm just going to say 2 thirds. You know what, I'll write 1 minus a third here. Like that. And we know d, right? D was given to us, so I just need to solve for x now. And so plugging in the value for d that I got was 1.5 meters, so 1.5 squared minus 2 times 1.5. X plus 2 thirds x squared, and just plugging this into a calculator, I get degree 2, so it's going to be 2 thirds minus 3 x 1.5 squared is something, so 2.25. So I get that x is equal to 3.55 and x is equal to 0.951. So what that's telling me is that there's two positions. So the total distance d, someone's got their mic on. Total distance d here. I realize I made somewhat of a mistake, but not really, because it's okay. It's just kind of backwards. Yeah, not actually a mistake. No, maybe I made a mistake. Let's see. So one of these, and let's see if one of these is the answer. If not, then I see where I made a mistake. So let's take a look. No, I should have the answers open already. So this is,
yeah, it's 0.951 seems right.
0.951.
Yeah.
Yeah, that's right.
The other one's larger than D anyway, so it wouldn't make sense.
Yeah, it wouldn't
I
make
guess it wouldn't
sense.
make sense. Okay. Yeah. So I just want to point out something. Yeah. Okay. Good.
Yeah, Namikaze also got 0.951.
Okay. Good. 7.951. Yes. Okay. So the answer to A is 0.951 meters because 3.55 is way past here. It would be like you're like over here, right? And somehow still that so it would be over here, and that's fine. It's just that the bead is on a slide on a rod, and the rod is just between these two charges. So it has to be an answer inside this range. So 0.951 is the only answer.
Can you go back
The
down
other
to?
answer is also correct.
Down here?
No, the
It's
other
just
answer
not on the
can't
picture
be.
that I showed us.
The other
Go ahead,
answer
sorry.
is just not on the rod. This bead is on a rod between the two, so the rod stops here. It's between here and here.
Yeah. But the electric field is still zero at that position, right?
Yeah.
Like at
No,
that place.
It wouldn't be.
because
Yeah,
they
it
both
would be.
if it's outside of the bead or if it's outside of the bar, and it's two positive charges, they're both going to end up pointing in the same direction. They
That's
wouldn't be able to
true.
cancel.
That's true. Okay, so what the idea is that they're equal here. They're not canceling, they're equal. So right here is just another position where the two electric fields, both point in this direction, one and two. It's not that they cancel at this point, it's just that they are equal at that point. That's all we were trying to figure out. So they're equal here and opposite, and here they're equal and in the same direction.
Can you scroll down for a second, please?
Yeah.
Wait,
Yeah, I
so it
wanted
can
to.
be-
Oh, okay, someone else can go then.
Oh, I'm asking. It can be stable then, right?
Yeah. It can be stable if what? If let me think for a second.
It's at x equals 0.951.
Yeah. It can
I
be.
bet.
I don't see why not. I feel like they
Since
want
the
to.
force is on Q, and it's just F equals QE, it can be stable because of that.
Mm-hmm.
Wait,
The Q would be.
what do they
constant,
mean by
so-
stable here?
Is it stable if it's positive?
Like if the
charge?
force, like what we
Yeah,
did with
isn't it
electrical field.
stable when it's positive? Because like then it just repels the two.
Yeah,
Right? So if
But
it's
as soon as
negative,
it
it'll
moves
be
closer to another bead,
it will be.
I guess it
unstable.
get pushed back. Yeah, it would have to
Yeah.
be stable.
yeah, it
It would have to be
repels.
stable, yeah.
Back
Okay,
to the
stable.
same position.
The
have
answer
a
is
question,
actually
but-
it's stable if it's positive. So if it's negative, what would happen? Well, just the directions would flip. So I don't really see how that wouldn't be stable because it would just, if it was negative, then it would, it'd be attractive. It'd be attracted to both. Yeah.
Yeah, but as soon as it got closer, it'd be attracted stronger to the closer one, and that would be an exponential increase.
Oh, okay. I guess so. Yeah, it's more attractive. Yeah.
Wait, I have two questions.
Yeah.
So number one, so since we're doing force, wouldn't we have to multiply E1 and E2 by Q, or we would have, but like it just cancels out, so it doesn't really matter.
It doesn't really matter. It doesn't matter. All I want to know is where does the electric field equal? Where are the two electric, like the electric field from here, equal to the electric field from here?
But what? Well, yeah, but it would cancel, wouldn't it?
It would
The
cancel.
reason
Yeah,
it
the charge
cancels-
on here. Yeah.
Because if you put
Because we're
that,
talking about the charge on Q. So the force on Q, that's what we're talking about, and that Q is on both sides either way.
wait, because like,
That's
wouldn't the
equally
force be
Sorry, what?
KE 3Q squared over X squared? That would be if you like put them together, right? It'd be Q.
Wait,
KE.
Could you scroll down to like the middle of the calculation real quick?
Wait, yo, who said exponential force?
Right there. Thank you.
Wait, this confuses me a bit too. So like,
Mhm.
if you wouldn't you multiply both sides by 3, so then I'm a bit confused on what happens here.
Where here?
Yeah, because it wouldn't be 3D squared plus 6xd plus 3x squared. Why is it?
You could do that, or you could do 0 equals d squared minus 2xd plus x squared minus x squared over 3. And then that factors into this.
This is what I was going to mention as well. Is you can if the equation just above, before you expand, see how you expanded the right side to its like quadratic
Yeah.
form. Right above that, you could probably just square root both sides, and you'd end up with the same answer.
That's true.
Because if both x is there squared, that's the only, we know all the other numbers and we know they're all positive, so you don't end up with like a,
Yeah. Yep.
you're not going to end up
Could
with
have done that.
plus or minus.
Could have done that for sure.
So then you just did that, and then the rest is just like finding the zeros. So you just plug in 5 for D, and then you just like stop for X.
Yeah,
Yes?
plug in D. Yeah, plug in D and then solve for X. That's right. Yeah. So
And then we
only
know
with yeah, sorry, go for it.
we know it's the second one because it can't be like over 1.5 meters.
Yeah, it can't be X can't be bigger than 1.5, so it has to be this one.
Oh, thank you. I just was a bit confused. I might make sure
I
it's all
understand.
clear.
Yeah, I understand. Yeah, for sure.
So,
I did technically make a mistake. Sorry, okay, you go, Ronak. Yeah.
Sorry. So just to clarify, at that bead, that's where equilibrium is, or is it just in the middle of the rod? Because that's what I was confused about when
Well,
doing this question.
if the bead was at 0.9, so if this is 1.5, then this is 0.75. So 1 point. Well, I guess that is where approximately where 0.951 would be, right? So only at that point is it an equilibrium. Otherwise, it's not. It's just not an equilibrium. It has a bigger force in a certain direction.
Oh, okay. All right.
Right. So I should have mentioned something. The mistake that I made is that the electric field points away from a positive charge and towards a negative charge. So the electric field on this point right here, so they didn't change the answer. The answer was fine because we're just setting them equal to each other, so it doesn't matter. But the electric field from this points in this direction because the electric field always, so this is E2. And the electric field from this charge points in this direction. That's E1. It didn't change the answer. I'm still looking for when those two things are equal. It's just to make a quick, not have something wrong here, is that E1, the electric field caused by Q1, points away from the positive charge. And E2, the electric field caused by Q2, points away from this positive. They always point away from positive charges. So yeah, that's that. Which also makes sense, because like if that's a positive bead, it would be repelled by this. It wouldn't be attracted by it. It would be repelled by it. So the force should be away, right? Again, didn't change the answer. I was still just looking for when those two things were equal and the same number, but that's it. Yeah. Just a label. That was the only mistake. Just a label mistake. Okay, so good to move on. Don't know where I put my.
We have one more question. I have another question.
Sure.
So I don't know if you mentioned this, but I did the question 2. I think I got what you got, but I got negative values. Like, why is? Because I got exactly the same roots, but they're both like negative. So why is that?
Do you have this exact same quadratic?
Oh, it's all multiplied by like 3 because I didn't do the exact same. But it's because I did the.
Okay.
I multiplied it by 3 and then subtracted x squared. So give me like I got 6.75 plus 9x plus 2x squared. So it's a bit different, but it's the exact same number. It's just like it's negative.
It's supposed to be minus 9x.
Yeah, it's minus 9x plus 6.75, I think. Yeah.
I'm not bad. Sorry about that.
Okay, don't worry. Very good. I'm happy you figured it out. Okay, next question is number 10. So I'm happy that question went okay. Let's take a look at number 10. So number 10 is 3-point charges lie across a straight line as shown in figure this, where Q1 is that, and Q2 is that, and Q2 is that. Separation distances are D1 is that, and D2 is that. Calculate the magnitude and direction of the net electric force on Q1, Q2, and Q3. Okay, so let's start with Q1. So the net electric force on Q1, there's two electric force. Yeah, electric force. Okay, so quick mention, F equals QE, right? And again, E, the magnitude of E, is KEQ over, absolute value of Q, over R squared, right? So, well, we want to find the net electric force, so we're going to have to add up two forces. So Q1 has two forces acting on it. One, which is caused by this, so it's a force in this direction, which is, I'll call it E2, the force, the field. Just think about the field for now. The field caused by Q2. And then E3, which is in this direction. E3, which is the force caused by Q3. So now I want to, the net electric field, it's in black, the net electric field is just going to be E1, or E, if I call this the positive x direction, then it's going to be E3 minus E2, right? E3 minus E2. And so let's figure what that is. Okay, so E3 is going to be KE, magnitude of the charge causing the field, which is Q3. So Q3 is -2 nanocoulombs or microcoulombs, but we take the absolute value. So it's just going to be 2 times 10. Well, you know what? I'll just leave it as Q3 for now. Okay, and what's the distance between them? Well, it's just D1 plus D2 squared minus KEQ2 over, what was the distance here? It's just D1. So D1 squared. I just want to put the square brackets like that. That's the net electric field. And then the force that's acting, that this Q1 experiences, is going to be, well, Q1 is a positive charge, yep. So it's just going to be Q1 times this. So this is E net. So the force is going to be Q1 times this, times KE over, well, KE Q3 over D1 plus D2 squared minus KEQ2 over D1 squared. And yeah, plug in numbers. That's everything after this, I think, hopefully. So let's see. Q1 is, do I take absolute values? Let me just think for a second. No, I don't take absolute values. I take absolute values of these charges. These are absolute values. This one's not absolute value, but that's okay. It's already positive, so it's fine. Yeah, so then okay, well, Q1 is 6 times 10 to the negative 6 times KE, which was 9 times 10 to the 9. Is that what it was? I forget what it was. KE is 9 times 10 to the 9. So 9 times 10 to the 9. Q3 was absolute value 2 times 10 to the negative 6 over D1 plus D2. So D1 is 3 centimeters plus 2 centimeters, so 5 centimeters, which is 0.05 meters squared, minus 9 times 10 to the 9. Absolute value of Q2 is going to be 1.5 times 10 to the negative 6 over D1. D1 was 3 centimeters, so 0.03 squared. Okay, let's plug this in and see what happens. So it is 6 times 10 to the negative 6 times the fraction 9 times 10 to the 9 times 2 times 10 to the negative 6 over 0.05 squared minus 9 times 10 to the 9 times 1.5 times 10 to the negative 6 over 0.03 squared. So I get that the net force is negative 46.8 newtons. It's all in the x direction. So that means in the negative x direction, 40, what did I say? 46.8. And, oh, there's no answer for 10, so let's look it on Slater. Slater, is there Slater solutions for this? Yes, there is. Oh, I hope so. We are in chapter 20. No, it's a different edition of the textbook.
Same answer I got.
Same answer you got?
Doesn't mean we couldn't have both done it wrong. But.
Yeah.
Yeah, it's the same answer. Yeah.
Wait, I have a question.
Yeah.
So can you just use the other equation? F equals KQ times Q2 over R squared. And then add them up.
Q times Q2. Yep, you can. Just remember the negative sign. Negative sign on one of them.
Yeah.
That would be the same thing.
This is the right answer on Slater, by the way.
It is? Okay, good.
Yeah.
There's volume 10 on Slater?
Pardon?
There's like
Yeah,
volume 10.
I could send it. Here, I'll send it.
Could you? Because I can only see volume 9.
Here, use
Thank you.
no problem.
Let's take a look. Where'd you put it? Sorry,
Wait,
discussion?
so if you were...
Yeah,
Oh,
just go
what?
to discussions.
Yo.
Yeah, go for it.
So if you were to do this with the KQ1, Q2 method, you would just straight up be like, F equals KQ1, Q2 over D1 squared minus KQ1 Q3 over D squared. D2 squared, right?
It would be, I think you have the if you did, okay, so then if you think about it like that, there's two forces acting on it. So there's a one force that acts this way, which has a
Oh yeah, that was positive.
This would be, since you're taking the absolute value of all the charges, then this would be negative. So this would be this quantity here. It's just multiply. Oh, it's this really. I'm just multiplying by Q1 here. So it's the same thing, right? So just if I were to just stick a Q1 in here, that's what you would have.
Alright, bad thing.
Right? That's what you would have. And that is what I did. I just multiplied in the front. Yeah, go for it.
Sorry, could you go over like the E3 minus E2 part again?
Sure. So, well, there's two charges that cause an electric field vector right here, right? Oh, good. Thank you. Someone sent check answer. Thank you. That's good. So what are the two vectors from the two electric fields? Well, we have one caused by this charge right here. It's repulsive because the that's kind of, I don't know. Sorry, that's kind of like funny to say. It's disgusting. It's repulsive. Anyways, so we have one repulsive force right here. And so this is going to be pushing in this direction, right? That's the vector that's going to be caused by this one right here, the repulsive electric field. Then we have another one that's attractive. So we go this way from that one. So this is the electric field caused by charge 2. This is the electric field caused by charge 3. And I define this as positive x, so it's E3 minus E2.
So E3, that's the thing. That's because it's the positive at the end is attracted to like the negative at the end.
That's right.
Okay.
That's right. Yeah.
Okay. All right.
That's exactly right. Okay. So yeah, that's question 10. Any questions about question 10?
So would you like really explain the bit? So could you explain the bit? So I would only doing part A, right?
Oh yeah, sorry, I just realized there's part A, part B, part C. I forgot about that. So I'll do at least part B again. Yeah.
They're just the
So
same,
part
just
A
with
is-
different numbers.
Yeah, they are the same thing, but so maybe I'll just do B. Maybe I won't do C, but we'll see. Or maybe I'll just do C actually. Let's just skip to C.
Wait, so let me.
Yeah, Erwin, what was?
So I'm trying to look at it. So then you do. So I get what you get E3 and E2, but then what's the difference between E3 and E2 in the sense that like if it's from the same particle, how are they different?
They're not caused by the same particle though. E2 is caused by charge 2. E3 is caused by charge 3. E3 is caused by charge 3.
So then you have to, and then why do you subtract them?
Because this is positive x. I define this as positive x.
So then you subtract E3 because E3 is the one that goes to positive X, and you subtract the one from positive Y.
Yeah, well, but like I subtracted E2. E2 is the negative one because it's going in the negative direction.
I think I get it. So basically, to get straight, so you're doing E3 minus E2 because E3 is the one that goes to positive X direction.
Yeah.
And then you're just multiplying everything by Q1 because you're doing the thing on the Q1.
Right? At the thing that the field is acting on Q1, so it's going to experience a force Q times E.
Correct.
Q1 is going to experience a force Q times E.
Right? Okay. I think I get it.
A note to make is that the force between two charges is the same. So the force on Q1 by Q3 is the same as the force on Q3 by Q1.
That's true. Yeah.
And it's all plug and chug. Like it's not much to like think about. Just like all plugging and chugging.
Yeah. So I'm gonna do C, but I'll
magnitude. Magnitude. That should be an important note there. Magnitude.
Yeah, magnitude is the same. Okay, I'm gonna do C now. So that's the charge. The force acting on Q3. So I'm gonna do that because it's the negative one, so it's gonna be a little bit more complicated. Not really more complicated, but just gonna do that. So X, that's the positive X direction still. So, well, it has two things acting on it. Both are attractive though, right? So it has one. I'm gonna draw them kind of like that. So one attractive E1 and another attractive E2. So you know what? Just for the, well, no, I'll still define that as positive. So the net electric field, E net. So for C here, E net is going to be negative E1 minus E2. Right? Negative E1 minus E2. They're both in the negative direction. But let's do it, let's do like the force way. So it's going to be F, like what people were mentioning before. It's the exact same way, really, but just so it's here. So what we really care about is the force of Q1 on Q3. That's negative. Or no, it's a negative. Yeah, we don't actually have to worry about the force like this. So just the absolute value of the force. Oh, that is negative. Okay, you know what? Let's just do it this way. Let's just do it. Let's just do it like this because I think it'll avoid a little bit of just writing notation problem. So we just have here E net now. E net is going to be negative E1. So E1 is the electric field caused by charge 1. So it's going to be negative KEQ1 over the distance here squared, D1 plus D2 squared. Okay. Minus KEQ2 over the distance here squared, which is just D2. So D2 squared. And then the force, F, the net force, is going to be the absolute value of Q3. We want absolute value because Q3 is a negative charge, but I already accounted for the direction with these negative signs here. Maybe it would have been better to account for it here, but just to match with the diagram, just so I can draw the arrows in the right direction. We know it needs to be pointing that way, so this is just absolute value now. And it's just going to be Q3 times, so, and I'll factor out the negative too. Well, to avoid confusion, actually, I won't. Q1, these should all be in absolute values. D1 plus D2 squared minus KEQ2 over D2 squared. That's the values. And this will be the force. That's that. So this will be the force on it. And I can just plug everything in here. So absolute value of Q3, I won't write everything out this time. So 2 times 10 to the negative 6 times...
Factor out KE and negative, so it's like easier to type into the calculator.
I guess so, yeah. I'll do that. So negative 9 times 10 to the 9. Yep, times. So just Q1 over D1 plus D2. So Q1 is 6 times 10 to the negative 6 over 0.05 squared plus Q2 over D2 squared. So Q2 is 1.5 times 10 to the negative 6. Yeah, over D2 squared. Is that what it was? D2 squared. So 0.02 squared. So I get that the net force is negative 110.7 newtons.
Yeah, I got it too.
Same thing? Okay, good. Thank you. We'll just check here too. Yep, that's
Yeah, that's right.
That's good. To the left, yeah, exactly. Okay, so that's that. That's question 10. Any questions before I move on to question 15? Okay, I'll take that as no. So, but anybody, you can stop me if you want me to go back or anything like that, or you can ask in discussions too. I should have discussions open actually. Okay. And thank you for the check answers again. So good, yeah. Discussion's open, so if you want to ask a question, discussions, I'll see it there. So, am I recording? Yes, I am recording. And your voices are in it. That's fine. Okay, we're good. So, what are the magnitude and direction of the electric field that will balance the weight of A, an electron, and B, a proton? You may use data in table. After this diagram real quick. Which diagram? This one here? Someone's asking for explaining diagram. This one here? What, like where, like these vectors, or what part of the diagram? Like these electric fields that I just drew? Is that what you're confused about? When we did Q3? The electric fields. Yeah. So here, these Q3s. Well, it's just that they're both. This is a negative charge. It's going to be attracted to both the positive charges. So the electric field is going to point in that direction for both of them, for both of the fields. Which also means the force is going to point in that direction. So I already accounted for the negative here. That's why I'm doing absolute values for everything down here, since I already accounted for the direction with these two negative signs. So the electric fields both point this way because this is a negative charge, and it's attracted to both these positive charges. So yeah. Okay, no problem. So what are the magnitude and direction of the electric field that will balance the weight of A, an electron, and B, a proton? You may use data from... Okay, so... Let's see. Magnitude and direction of the electric field that will balance the weight of... We did a WebAssign problem like this, and I was very confused with the WebAssign problem too. I forgot how I did it now. The wording of the question is a little bit... Yeah.
It will, the net force will be equal to 0, so just the gravitational force will equal the electric force as well, and that's it, I think.
Oh, okay.
That's
so
how
the okay. So the gravitational force acting on an electron, so part A, is equal to the gravitational force. Sorry, the electric force also acting on that electron.
Yeah. So there is no motion. I think that's it.
And we're asking what's the magnitude and direction of the electric field that will bounce. Well, direction would be up, I presume, assuming the
depends on the charge.
Oh, that's
depends
true.
on the charge.
Okay, yeah.
I think that's it. Because it's asked for an electron and a proton. It is usually up because we use a positive one.
Yeah, that's true. So for an electron, Q equals E, negative E. I mean negative E. So then we have. Let me see this here. Yeah, negative E. Good. Then here we have M, so mg equals QE, Q times the electric field. And we're solving for this magnitude. So mg over Q equals the magnitude of the electric field. And I think we just plug everything in. We know this. I assume we know this. On Earth, I assume, do we just say this is 9.81? I forget. And then Q is, yeah?
I think it's 9.81.
Yeah, it is 9.81.
Okay. And then here we just say the absolute value of Q, and then we decide the direction after. So we have an electron. In fact, I'll draw it in red, so it's an electron. It has two forces acting on it. It has a force going down and a force going up. So the only way you get a force going up, right, is if there is a positive charge here, right? There must be a positive charge here that's creating an electric field, right? So that means that the electric field will be going down. So both this right here is the electric field, and this blue one is the gravitational field. Sorry, gravitational force, and this is the electric force, I should say. That's the force.
I think gravitational field's also technically true.
Gravitational field would be right, yeah.
Sorry for interruption, but this is, you were right. The red one is the electric field. The gravitational force is up because it's an electron.
But if this is the gravitational force doesn't change if it's negative though.
No. I'm not. This is an electron.
This is an electron.
I'm sorry. The electric force is the electric field. The electric force will go up.
Yeah. Oh yeah, you're right. Hold on. Yeah, that doesn't make sense. The electric. You're right.
The field lines need to point down, but the force needs to point up.
Exactly.
That's what it is.
Yeah.
Good. We figured it out. So thank you. So we know we got to figure out the magnitude, and then the direction is just going to be straight down. Yeah. Question.
Yeah, I have a question. Basically, how did you get the equation FG equals FE? I just didn't understand that part.
FG equals, well, this is just saying what magnitude of the electric field will balance the weight of an electron, right? So that just means what that's saying is like what magnitude of the electric field will produce a electric force that is equal to the gravitational force. That's what it means by
Oh,
balance
so
the
you
weight.
have to set them. All right, so you have to set them equal to each other then.
Yeah.
All right, thank you.
Exactly. So we get the magnitude like this, and we get the direction like this. Right, yeah.
Quick question. So the diagram that you just drew. So why is the force of the electricity pointing up and then the thing pointing down?
Clear. That's a positive charge.
It's a positive charge. Oh, okay.
That's our electron. I'm just saying, you don't have to think about the positive charge. It's just like we know it has to balance, so that means that there's a force of gravity going down, so an electric force has to be going up, and it must be caused by a positive charge here.
Yes, because it's attracted, right? Because
Right, yeah.
electrons are active, yeah. So, and then the energy would just go down. Why exactly?
What would go down?
You know how you said like E was going down, so why is that?
Oh, the electric field? The electric field here?
Yeah,
electric field always points away from the positive charge. Always points away from the positive. The force doesn't, but the electric field always points away from a positive charge. So the electric field's going down, right? So the direction of the electric field is down. Right? The direction of the electric force is up, but the direction of the electric field is down. Because again, it has to point away from a positive charge.
Okay.
Right? So this is magnitude over here. Mass of electron is 9.1094 times 10. I lost it. Where is it? Mass of electron times 10 to the negative 31 times 9.81 over E, which is 1.6022 times 10 to the negative 19. So let's plug that in. 9.1094 times 10 to the negative 31 times 9.81 over 1.6022 times 10 to the negative 19. So I got 5.5775, I guess, times 10 to the negative 11. That's it. I guess it's in newtons per coulomb, right? I guess it's in newtons per coulomb. And so, yeah, let's check that answer though. 15. Oh, someone sent it. 5 point, and yeah, so then I have to just also put so we got the right magnitude, and now there's the direction. Well, if I define that as positive, then this is negative. So it's going down this amount. Right? So I'll just say down. And that's our answer. Right? I could have left the negative sign in there too, but it's good to just keep the magnitude. I mean, that's really what we want.
Yo.
Yeah.
Can you summarize what you did?
Sure, yeah, sure. So, well, how about I do part B, and that's going to be, I'll explain it all from the part B is essentially the same thing, but just with a different charge.
Same thing, just proton. Yeah, never mind.
So I'll do it like that. And then if you still have a question after, just, of course, I'll go over it.
I bet. Thank you.
No problem. So for part B, it's going to be the same thing. We have now a proton, right? We have a proton here. It has two forces acting on it. It has a force of gravity down, right? And it has a force, an electric force pointing up. Okay. That electric force, okay, so Earth is here, right? So what we first of all have to know is that Fe, the electric force, is equal to the force of gravity. We're asking, and so remember, electric force is the magnitude of the electric field, or QE, Q times the magnitude of the electric field, times mg. Sorry, equals mg. So the magnitude of the electric field is going to be mg over q, and just note that q equals E, because it's a proton, so it just has the magnitude of E. So this is mg over E, which is going to be the same number, I think. Oh, it's somehow not. Oh, a different mass, of course, different mass. So it has a different mass. So the mass of the proton is 1.6726 times 10 to the negative 27 times 9.81 over 1.6022 times 10 to the negative 19. And that will be 1.6726. So I got 1.024 times 10 to the negative 7, which is good. That's fine. Newtons per coulomb. And now the direction we have to think about. So the force, on a positive charge, right, the electric field and the force are going in the same direction, right, on a positive charge. Because remember, Fe vector is QE vector, right? So on a positive charge, if Q is positive, the force that the charge that the force is acting on is positive, then we know that the electric field and the force must be going in the same direction. So the electric field goes up. Probably a better way to do it than what I was talking about with like adding a charge here and talking about that. Just think about, are they going in the same direction or opposite directions? In the case of a positive charge, the force and the electric field are going in the same direction. In the case of a negative charge, they're going in opposite directions because look, Fe, right, is equal to negative something times the electric field. So this is a vector. You're multiplying it by a negative number, so it's going to flip directions. For a negative charge. This is a positive charge, so they're just in the same direction, so this is up.
But I get the math behind it, but like, can you like explain to me again like the field part? Because like I get the gravity goes down because it's gravity. The electric force goes up because it needs something to bend. But what's like with the E, like the electric field? Like what's up with that? Like,
well, the electric field, right? The electric field is what's causing the electric force, right? It's what's causing the electric force here. So if we have, like, they don't necessarily go in the same direction, right? Because up here, the electric field was going up. Sorry, the electric force was going up, but the electric field was going down because the electric field always points away from a positive charge. Right? So it's better to start over here. We have a positive Q, right? So if you have a positive Q, the force and the field go in the same direction. That's the main takeaway here. It's a positive charge. Otherwise, if it's a negative charge, they go in opposite directions.
Because for B, there'll be a negative charge above the positive charge to like attract it. So E goes up because it goes towards the negative charge. It's like up, and for the other one, there's a positive charge up, so it goes down.
Yeah, exactly.
And the direction is just E.
What do you mean direction?
Like the direction of the whole thing, like because this is up. It's up because E goes up.
Yeah, the direction of the field is up, and the direction of the force is also up because we're acting on a positive charge. If this was a negative charge, the force would go down.
Okay, I think I get it.
Erwin, remember that the force from an electric field has the magnitude of the electric field. So the direction of the electric field does not influence the direction of the force. The direction of the force is influenced only by the sign of the charge. So if it's an electron and has a negative charge, it'll go opposite to the direction of E. Right? But if it's a proton and it has a positive charge, it'll go in the same direction. The issue is that the thing between gravity and electric charges, we don't have negative mass, but we do have negative charges. Otherwise, negative mass would behave the same way as negative charges would in electrical fields.
Yeah, presumably. Okay, so is that?
Yeah, that makes sense. I think I got it.
Wait, can you scroll up to the question for a second?
Scroll up to the question here, yeah.
Oh, so that's the reason you equated the gravity and the electric force, because it says balance the weight, so you want it at... Okay, all right, thank you.
That's it? Yeah. No problem. Okay, any questions? Yeah.
For part A, how did you know that they wanted the proton on top?
Well, yeah, that's not really the best way to like. This probably is like a more confusing way of doing it. All we know is that we have an electron. We have an electron here. There's a gravitational force acting down, and there's an electric force acting up. That's all we know. And so the magnitude we find like this. But the direction, well, remember, probably your camera's in the way. F equals QE. If Q is negative, then the force will be in the opposite direction as the electric charge, electric field vector. Right? So since E is negative, and the force is going this way, that means the electric field must be going this way. A way to think about that is that the only way an electron could be pulled up is if there's a positive charge up here.
Or if there's a negative charge underneath it.
Or if there's a negative charge underneath it. That's true. So again, that's why it's not actually, this isn't the best way to do it. Either way, if I do either of those examples, either of these two cases, the electric field points away from a positive charge and towards a negative charge. That's the main idea. Right? So it'll point away. I mean, no matter what, it's going to point away from this negative charge, but it's always going to point towards a negative charge and away from a positive charge.
I have a question. For the formulas, where do you get all these formulas from?
The formulas? Well, I have it in my notes. I also just have a formula sheet in front of me. So.
Do you use the formula sheet? Because I found the formula sheet, the one from they gave us is pretty empty.
Is it this one?
Let me take a look. Hold on. I don't see. I think
that's the fourth one, yeah.
I'm blurry. I think so.
Okay, so
that's the fourth one.
That's the one that I'm using here.
There's a formula sheet posted in, I'm gonna either say discussions or homework help, that is like made. I forget who made it. Someone on the Discord made it. That might be better. I think Jasper made it. And it's all like sorted by chapter. So if that helps you more.
Wait, I have one I have one in the homework help that Adam has, but I don't know if it's the right one or no. Is it by Adam or no?
No, I mean I didn't post. I have my notes posted, so you can go look at that's there, but not a formula sheet that's nicely made. I have
it says formula _sheet 4, and it's posted by you.
Oh, but look at the date on that.
Oh, okay.
That's for the last midterm. The first midterm, actually. It's for the first midterm.
So let me see if I can find it, because I really want to have the formula sheet available. Can someone repost it or something, or?
Yeah, I can do
it.
It should be pinned. I'm pretty sure. Check in pins for homework
help. The one that I have,
discussions.
or the one that Jasper made.
I just posted Jasper's in discussion.
Okay.
Yeah, the Jasper ones, they're in pinned messages on discussions.
Is this one? Wait, formulas and stuff. I think I found it.
I just sent in homework help. I just sent the one that I'm using.
Brian, I will send you that one. I will just send it to you right now.
I'll keep moving here. You guys can figure that out. So that's number 15 done. Next one is number 17 for us to do. So number 17 is here. Oh, by the way, we're taking a break at 6:30 and 8 o'clock. Those are the two breaks we're doing. So, yes, we're almost at our first break. So, two equal positively charged particles are at opposite corners of a trapezoid as shown in this figure. Find symbolic expressions for the total electric field at A, the point P, and B, the point P prime. So just symbolic, we don't know any numbers except a few angles here, but we could even do without the angles. It doesn't really matter. For the P prime is here and P is right there. So we want to find the electric field at those points. So remember, electric fields always point away from positive charges. So it goes like that and like that, right? That's E, call that E1. I'll call this one E2. And so now we need, so that's kind of like this, like that, and that's kind of like that, right? So we want to figure out the magnitude of these, just the magnitude, I think, right? Find symbolic expressions for the total electric field at those 2 points, yeah. So this is going to be, this is also 45 degrees, and this angle isn't necessary right now. So, well, let's start. We know that total electric field, I think we just take the magnitudes, and then we take the x and y components. Do we need x and y components? Yeah, we do need the x and y components separately. That's going to get really messy. Let me see the answer quickly.
I know it. Took me like 20 minutes to finish this one.
Yeah, so it is as messy as I think it's going to be?
Yeah.
It is.
Also,
Okay.
part B is gonna give you depression.
Okay, so let's see.
I posted the first part in discussions. You can look at that if you want.
Okay, thank you. Yeah, I probably will. But let me just give it a try first, and then yeah, I'll give it a try first and then see. So, okay, well, let's start. So at point P, we have the two electric fields. So the magnitude of the first one, magnitude of E1, is KE times the charge creating the field, which is Q. Someone's got their mic on. Abdul.
Oh, sorry.
Don't worry. So KEQ and then over R squared. So we need to find the distance between here and here. Well, that's conveniently just D. Okay, that's just D. Okay. Then we need to find the E2 is KE equals KEQ over, sorry, D squared. Squared on the bottom. Over this distance squared. Now, what is that distance? Let's try to figure that out.
I think I know. I have an idea.
Sure.
So now you know how they're like symmetrical and they're one on top of another. So I'm guessing distance will only be 1.5 because you have D and then because it's like the bottom one is 2D, right? So that means it's kind of half a D and then another D and then half a D. So like the second one is just 1.5D. Do you see my logic?
Oh, okay, pretty much. Yeah, I think I do. Yeah. So we know that here to here is D. That means that this plus this must add to D. So each of these are one half D's. 1/2 D. So from this we can find, what can we find? We can find, we know an angle. Yeah, we know an angle and a side, so we can find this side right here.
No, don't you just have to say 1.5D?
We need this length. We need this length here.
Oh my god.
Right?
Well, you can just do sine or something, or
yeah,
cos.
Yeah, adjacent over hypotenuse. So cos 45 equals adjacent over hypotenuse, which is this R that we care about, right? So R equals D over 2 times cos 45. Cos 45 is 0? No. Cos 45 is root 2 over 2. That's what I thought.
Yeah, root 2 over 2.
So D over root 2, and that's that. There you go. D over root 2. That's R. So then this is going to be D squared over 2. Because R squared on the bottom. So it's D squared over 2. So then I can just say that this is... hold on. That quantity with the 2 go up here. Yeah. Well, yeah, go for it.
Oh, it's really random. Wait. For the cos 45 part, would it matter if you did sine 45 since they both equal the same thing, right?
It wouldn't matter. Why wouldn't it matter though? Oh, because
there's 45.
It's a special triangle.
Yeah, it doesn't. Yeah, because it would be opposite over hypotenuse, and you don't technically know the opposite side here, but you do because you know it's a 45, 90 triangle, so it's okay. But we don't explicitly know this side.
Yeah, thank you.
Yeah. No problem. Okay, so leave that in brackets there. So from here, we do. These are the magnitudes. To find the actual net, the magnitude of the net electric field is going to be the square root of the x value of the electric field squared plus EY squared. Okay, that makes sense to me. So let's figure out each of these things. Well, what's in the x direction? In the x direction, we have, so EX is going to just be, well, it's going to be E1, entirely E1, so KEQ over D squared. And then it's going to be minus KEQ over D squared over 2 times cosine 45, right? Cosine 45. So that's good. Which we know is root 2 over 2, but it's okay. We can leave it like that for now. And then EY, well, that's just going to be, again, I'm just defining this as positive. So all I have is, I only have one force, and it's just going to be, or one field, so it's going to be KEQ over D squared over 2 times sine 45. Which will simplify to KEQ over D squared minus root 2 KEQ over D squared. And similarly, this will simplify to KEQ over D squared over 2 times root 2 over 2. So it's going to be a root 2 here. And it'll cancel with this 2 right there. And so there's our components. So the magnitude of the net electric field is... Oh, you know what? No, we don't have to do it like that. I realized the answer in the book is in I hat and J hat, so we can just do it like that. So we know the X and Y components. Just going to check if this is fine. Okay. So the net electric field is something times I hat plus something times J hat, right? So what are the somethings? Well, the X component is going to be EX plus EX, I guess not absolute values, just EX. These are absolute values. We don't need absolute values. I know, yeah, we don't need absolute values on those. This is EY. And so now let's plug all this in. So EX, I will factor out everything I can. So KEQ over D squared, I can factor out. So it's going to be KEQ over D squared times 1 minus root 2. Okay. I hat. Yep. Then plus root 2 KEQ over D squared J hat. And 4 root 2? Why is it 4 root 2? Oh, that's for B. Sorry, for B it's 4 root 2. For A it's okay. Yep, we're good. That is everything. Keep looking at the wrong question. Yeah, that's everything. Okay, so that's part A.
So, like the X and Y component, could you like explain that again?
Yeah. So how I figured out the X, so we didn't need this. I didn't need this because I'm not finding the magnitude of it. I just do it in unit vector form. So for the X and Y components, I just take like what's going on in the X direction here. In the X direction, it's E1 and negative the X component of E2. So this is E1 and this is negative the X component of E2, E2X. And then for EY, for the Y direction, well, all that there is in the Y direction is positive the Y component of E2. So that's just what this is. What did I say, 2Y? Yeah, E2Y. Like that. Does that make sense? Or do you want me to, any other questions about that?
So wait, I would just have to say that, but would I have to like give any like numbers or anything?
No. It said find symbolic expressions for the total electric field at these things. So symbolic expressions is all we need.
I see.
Okay. Then let's try B. So B is for this point P over there. So let me just get the picture again. And we'll do B here. So we're looking at this point P prime. So what are the two electric field vectors? We have a field vector going like that and a field vector going like that. Right? Like that. I'll draw them a little smaller so we can fit in the picture. This one I'm going to call E1, and this one I'm going to call E2. So let's find magnitudes of all these things. So E1, magnitude of E1 is, okay, magnitude of E1 is KEQ over D over root 2 squared. Same thing as before. We found that this length was D over root 2. D over root 2. So now we know that. That's that. And then E2. Oops. Oh boy. Can't write today for some reason. My handwriting is very bad today. Sorry about that. We have KEQ over just 2D. 2D squared. But the radius is just 2D there. Okay. And now, those are the fields. Now we just got to break it into x and y components. So EX is going to be, let's just do it generally here, is just going to be negative E2. Right? Negative E2. In fact, I'll do magnitudes here. Minus the magnitude of E1 cosine 45. So hopefully that makes sense. I'm getting the x component of E1. That red angle there is 45 degrees. Oh yeah. It's negative because it's going in that direction. So let's simplify this. It's going to be negative KEQ over 2, well, I'll say 4D squared, minus KEQ over D squared over 2. Someone's got their microphone on? Don't know. Someone does. Okay, we're good now. Thank you. So KEQ over D squared over 2 times cosine 45 is root 2 over 2. Right? So we don't need, well, I guess we do need brackets around that. So this will simplify into negative KEQ over, I should be clear, this is like a little e. It's not a variable e. 4D squared minus root 2 KEQ over D squared. That's our x component. So now our y component, we're going to need what's in the y direction. All we have in the y direction is negative E1 sine theta, sine 45. Negative magnitude of E1 sine 45, right? Which is going to be the same as the second term here, again. So negative root 2 KEQ over D squared, right? It's going to be the same as this. Because cos 45 and sine 45 are the same, right? So, yeah. Yeah, just making sure. So, yeah, that's good. I'll do this here. And so we have our x and y components. So now, just to find our vector E, well, it's going to be EX times I hat plus EY times J hat. So that is going to be, I'll factor out everything I can from this to simplify this. In fact, I'll do it up here. So negative KEQ over D squared times 1 over 4 minus root 2. So that's what that's going to be. What's going on there? Why did they do... Okay. Let's see what happens. Negative KEQ over D squared, 1 over 4 minus root 2, I hat, plus, well, minus root 2 KEQ over D squared J hat. And that should be pretty much the answer. It's not exactly the answer, but it is pretty much. So let's see what the difference in what they did was. Okay, so they did only a very they just did like a factoring thing. That's all they did. Like, look, if I, it's kind of weird that they did that, honestly, but if I factor everything I can out of here, KEQ over D squared, yeah, this would become negative KEQ over D squared. This would become 1 over 4 minus root 2 I hat plus root 2 J hat. and all they did was they multiplied top and bottom by 4 here. For some reason. They didn't have to. So multiplied, well, we'll see what I'm going to do in a second. So 4d squared. And then multiply by 4 everything inside here. This is just going to be 1 minus 4 root 2 I hat. Oops, too many hats. Plus 4 root 2 j hat. There you go. And that's the actual answer. You didn't have to do that. It's just like simplifies the fractions slightly, kind of. So yeah.
Okay, so my question is, so you know how like if you go back to a formula in some sense they're kind of like symmetrical, like these two dots?
Yeah.
If you figured out number A, would there be like a shortcut you could do to like find number B? Because isn't like the only difference is like it's 1/4 instead of 1 in the answers, and like it's negative. So like would there be any way to kind of shortcut this since they're so like similar and so like they're just like kind
I
of
know what you
mirror?
mean, yeah. Let's compare the answers we got for the two parts. Part A is here. So if I factor out a KE, Q over D squared, I would just get 1 minus root 2 I hat plus root 2 j hat. And I guess I can multiply by 4 here just to match what they did. So I'm just doing this to match the answers together. So let's look at the difference now. So I had KEQ 4D squared. Here it's negative KEQ 4D squared. 4 minus 4 root 2, 4 root 2. 1 minus 4 root 2, 4 root 2. So, and can we explain any of those easily? Let me think for a second. Well, it's definitely in the opposite direction. Okay, we know the negative here we could have explained. I don't, it's kind of a stretch. It would be too much of a stretch to say we could figure it out from the first answer, I think.
Yeah, because the negative that you said, it's just like it's kind of completely opposite direction. So it kind of does make sense that it is a negative instead of a positive.
But then, can you explain this 4 being here and a 1 in the next one?
So, the x component in terms of like from point P to point P prime, you notice the distance between the 2 points, like the distance between a charge and P for A is the distance D, and the distance between a charge and P prime is 2D. Like we're talking about just the x components.
That's true, yeah.
So we know that what's it called? The field decreases exponentially with radius.
Mm-hmm.
So 2 times increase in radius should lead to a 4x decrease in the field. So that's one way to get the x. The y, I don't think you could do anything.
Although
with
this
that.
is still a 4 here, strangely. It's not just divided by 4 somehow. There's a 4 here, and is that 4 supposed to be there? It is supposed to be there. So that what you're saying would make sense, I think, if this 4 wasn't there, because then it would just be divided by 4 on the x component. But there still is a 4 here.
Wait, what about the equation right above it?
It's 1/4 though. 1/4.
Wasn't the original one 1 minus root 2 plus root 2? Like
yeah,
part A.
Up here?
Yeah, 1 minus root 2 plus
true.
root 2.
And here it's 1/4. Oh, wait.
And it's not so the
So a 4 decreased by 4 is what I'm saying.
But not quite, because then you'd have over 4 here. If it decreased by, you'd have over 4.
Oh, that's true. Yeah, I'd have to be
Right?
over 4 there as well. Yeah.
4, right? So
wait, Kevin, are you talking about the increase or like the square root law, the inverse square root law?
we're just trying to figure out, is there a way to go from part A to part B just looking at it, just by inspection, to get the answer? And we can't figure out a way right now.
Yo, Adam.
Yeah.
For part B, did you make the left side positive x?
No, this is still positive. This is positive. Like that.
Okay, wait. Then I have a question.
Yeah.
So you said, wait. Can you scroll to the final answer?
Mm-hmm.
Okay. So shouldn't the root 2 part and the 1 part, the 1/4 part, shouldn't they both be the same direction?
These two here, like this.
Yeah.
These two things here.
Yeah.
Like, should they both be the same sign? Is what you're asking?
Yeah.
Well, they're both being. It doesn't particularly matter. I mean, if I figure out what that is, 1/4 minus root 2, that's a negative number, so it's in the negative direction. But then it's being. Oh, how's it being multiplied by? That's a negative value.
Because I'm saying, I think they should be the same sign. I might be wrong though.
Then let's
'Cause they
see.
both-
Well, let's try to figure out where that came from. Then it came from here, right? So I factored out. Yeah, they should be the same sign. You're right. This has to be a positive number. Oh, did I miss that? Did I just not read the answer in the book properly? Yeah, that is supposed to be a plus. That is supposed to be a plus.
Oh,
Yeah, good catch. Yes, that is.
Alright.
Right. Definitely did not see that. I just
Okay.
factored out this wrong here. So
Yeah, no worries, no worries.
okay. Yeah, thank you for that.
Okay.
So, okay, that's number 17. Are we good with that?
Could you go back to part A where you calculate the y component?
Part A, where I calculate part A here on the y component. Yeah, right here. So E2y. So this E2y, like the y component of E2. So if I look up here, E2 is coming from this charge. So I just need the y component of that. Right?
Okay.
So
Yeah.
to get that, I just do the E2 times sine 45. I wrote it out a little bit nicer on these ones, right? But yeah, now there, I'll box the way I did it here. EY is that, and EX is that, right? So we're gonna take a break now. But any last questions before we start our break?
No.
Okay. Sounds like no. Yep. Okay. Question?
You know, it'd be cool if you did for like the next study sessions.
What is it?
If you gave out the questions in advance, so like whoever wants to kind of do them and can like verify them on the spot with you.
Well, I mean, I'm just doing the practice problems in order. I'm just doing the practice like the suggested ones that the teacher gave in order. So anyone's welcome. That's how I'll do it. Yeah. So don't worry.
This quick question.
Yeah.
Are you doing any study session for the MTH? Because I don't think you posted it.
I am. I didn't post it yet. No, but I'll post it by the end of the week.
Oh, okay.
Okay. MTH and ELE if you're doing ELE.
10 minutes?
15. We'll do 15 minutes.
You're not doing anything from MTL because you don't take MTL, correct?
I don't take MTL.
No,
I don't. Sadly, I can't help you with that one.
That class is wild. Like
yeah.
Who wants to do the add-on for MTL?
Not me. Not me.
Not you. Okay.
Yeah. I think you're very lucky that you're not in MTL because MTL is like, it's an adventure.
I don't think there's someone understands the subject that's good enough to be an add-on for that class.
Yeah.
Yeah, everyone's confused in that class. Like that class.
You might be the only person, at least that I know of, that owns like more than one math textbook that wasn't a mandatory textbook at some point in your life.
Yeah, possibly. Yeah. I do own quite a few. Okay, guys, 15-minute break. I'll be back at 46. Okay.
You're also always ready to buy some Adam merch in the future, eh? I feel like Adam's gonna make it big, you know. You gotta buy that merch soon, you know.
Yeah, I don't think I'm going to be buying Adam merch. That just sounds a little obsessive.
Yeah, yo, I watched like 2 videos from Adam, and now my entire YouTube feed is just like Adam. You know what I mean? That's like
It's not like 3 blue, 1 brown or something like that.
Or what did you say?
It's not like 3 blue, 1 brown or whatever.
No, straight up, like I open up YouTube like right now, and it's Adam showed up. I'm like, damn, and I don't know what to say to that.
Are you saying the algorithm is doing good or doing poorly?
I guess it's whatever you can consider it. It's like good. I don't know. It's just like interesting that like Adam is popping up because I'm not subscribed to him. You know.
Wait, yo, who's Adam?
That's honestly a good question, though. Not even gonna lie. Who is Adam?
What is life?
Yo, I'm not even playing.
In case you are like serious, Adam's the person who hosts these sessions.
Oh, it's the guy that was doing the tutor.
It's the person that we've been listening to for the past hour or 2.
It's the person I've been listening to for the past semester.
Yo, Cameron.
Yeah.
Are you gonna do like an ELE sesh or no?
Yeah. I wasn't going to announce that yet because it's still like I'm also busy and trying to figure out my own schedule.
Yes.
Most likely, if I am gonna do one, I mean Adam might do one, in which case that would be fine. But if not, or if I plan to do my own, it will probably be on the weekend coming up. Don't think it would be. I don't know what anyone else is planning it for study sessions, but maybe like Saturday night might be good. It's tough because we have math right before
Yeah,
ELE,
exactly.
which is the problem.
Exactly. Yeah.
So what I might do is I might do Saturday night. I have someone, I forget when this was. This was in like the last lecture I had. Someone posted a link with quite a like I don't know, a handful of old finals. So I'd probably go over those because that's like the best material I can find. So old midterms, have the answers for them. And then maybe like the morning before the actual final. Like it's on Wednesday, or is it on? It's on Wednesday, right? Or is it on Tuesday?
27th, whenever the 27th is, so that's Tuesday.
Tuesday? Okay, yeah. So then I would probably do Saturday night, and Tuesday Tuesday morning before the exam.
Yeah, that sounds fine.
And we'll just do old midterm, or not old midterms, old finals, and that should be pretty good. And there's some stuff that's not necessarily on each. Apparently, like each midterm or each final doesn't necessarily cover all the material that can be on the final.
Yeah.
It like as an example, like you might not have any questions that deal with superposition. At least some of the finals don't have that, but I'll try to pick ones out that at least have the like they have sort of one of each type, and a Thevenin's, because that's like a big important one is being able to do a Thevenin's circuit or Norton circuit, like whatever, either one.
Yeah, that sounds.
Yeah, I will post that stuff. Probably I would say I will have a time. I'll talk with figure out when everyone else is doing one, and I'll have a time by Wednesday.
Okay.
Yeah.
Oh, you mean Tuesday, right? Not Wednesday.
No, Wednesday. This week, Wednesday.
Oh, this week, Wednesday. Okay.
Yeah. Like, I meant this week, Wednesday. I'll see if I can plan out the times. The thing
Or-
about the
Yeah.
Yuli ones is they're the question like it's one of those they're the types of questions where if something goes wrong at the beginning, it screws up your whole system. So and to confirm, if you didn't read the final information thing, I think you are allowed to use online calculators.
Yeah, that's
which
what I
is an
heard.
interesting. That's interesting, but I can't think. It won't help you too much, I guess. It only help you at the end when you have to find the answer.
Yeah, I think it would like help with like people who didn't have like a matrix, like I don't know, like you know how like some calculators could do like matrix stuff.
That would be most likely what it helps you with is
Yeah.
doing your final, like getting the actual answer.
Yeah, pretty much.
And there's like there for whatever reason there's chapter 11 questions. I don't think there's content in chapter 11 that's like assigned as part of the assignment questions, but not actually content that we're taught. And I'm not sure why that happened.
Do we or do we not do them?
So we don't deal with maximum power delivery in AC, although it's not hard to. It's not like a hard concept to grasp because it's sort of the same as it was in DC. But we don't do questions like that. And there happens to be like a good portion of the beginning of chapter 11 questions is those questions, maximum power transfer questions.
Yeah, I just have like one chapter left, and that's it.
Chapter 11 is the last chapter of the course.
Okay, everybody. I am back.
Welcome back.
So let's get into it. Thank you. Okay, there we go. So hopefully everybody had a good 15-minute break. We'll take another break at 8 o'clock. That'll be a 20-minute break. And then we will go until 9 o'clock after that. So let's see how much we can get done in the next little while. I have a little bit of a headache, so I'm going to put on my trusty blue light glasses. Not
Oh
only
no.
does it probably do nothing, but it also makes me look cool. So
It's that ad.
okay, let me just put them on 1 second. Can't hear for a second.
I swear, group, it's a thing.
There we go. Okay, good. Now I'm
Damn.
full gamer mode.
Looking snazzy.
Let's begin. So we were at question 17. So our next question is question 19 that we're gonna do. So let's start there with that question. Any questions before I start? Okay. Sounds like there's no questions before I start. Number 19.
Sorry, wait. Did you say 20-minute break at 8 o'clock?
Yes, 20-minute break.
Oh, okay. Wait, just want to make sure.
That's right. Okay. So, number 19. 3 point charges are located on a circular arc as shown in this figure. What is the total electric field at point P, the center of the arc? Find the electric force that would be exerted on a -5 nanocoulomb point charge placed at P. So part B is easy to find once we find the electric field that's at P. So we need to find the electric field at the center of the arc. Is my door closed? Yes. Well, we just need to find what the electric field is based on all these charges here. So we're going to have 3 vectors contributing to the electric field. The first one is this way. So I'll call that E1. The next one is this way. I'll call that E2. Not E squared, sorry, E2. And then the last one is this way, which I will call E3. Okay, and then that will be our electric field at that point. So the sum of all these will be the electric field at that point. It looks like it's going to go, well, it's going to go along the, it's going to go along the x-axis, most likely. It looks definitely that it's going to go along the x-axis in some way. I don't know if it's going to be the same. I don't know which direction. Probably positive. Probably out this way. So since that's the case, I'll just choose this. It doesn't matter which way you choose your positive axis to be, but I kind of want it to be in the direction of our answer. So that'll be like that. So now, let's start working on it. Yeah, let's just start working on it. So I'm going to find the magnitude. I guess all we care about is we know the y components are going to cancel out, right? We know the y components are going to cancel out. So all we care about are the x components. We know so let's first find the magnitudes of all the things. That's what we'll do first. We'll find the magnitude of E1, and then we'll decide on those things after. So the magnitude of E1 is KE Q1, and I'll just call this Q1, Q2, Q3. So it's going to be KEQ1 over 4 centimeters squared, so 0.04 squared. Good. And then that's fine. That's just what that is. We don't know this distance, strangely. I don't know how we're going to figure that out. Let me think for a second. That's a 3, and then that's a...
If it's a circular
it's an arc.
Yeah.
Then it's a radius of...
Oh, it's a radius. Yes, you're right. Okay, good. Yes, thank you. That's right. Okay. So E1 is this. Magnitude of E2 is going to be KEQ2. You know what? I'll just put the numbers in. So Q1 was 3 nanocoulombs, so 3 times 10 to the -3. And then this is going to be... I'll take the absolute value because I'm going to decide the directions myself. So I just want the magnitude. So it's going to be 2 times 10 to the -9 is nanocoulombs. -9 over 0.04 squared, and then the magnitude of the third electric field is the same as the magnitude of the first electric field. It's going to be KE 3 times 10 10 to the negative 9 over 0.04 squared. So, I'll find numbers for all these things. E1, which is, I'll find numbers. It's probably useful in this particular case. So it's going to be 9 times 10 to the 9 times 3 times 10 to the negative. Okay, so it's 9 times 9. I'm already this far into typing into my calculator, so that's fine. Over 0.04 squared. Oops. 0.04 squared. So the magnitude here is 16875 newtons per coulomb. The magnitude of E2 is, it's the same. The magnitude is the same for all of them. I just realized. Yeah. Oh, no, not quite the same. Sorry. There's a 2 there instead of a 3. Yeah. It's a 2 there instead of a 3. So this is just going to be 11,250 newtons per coulomb, 11,250 newtons per coulomb. And then E3, I don't even have to calculate it. I just know that it's going to be the same as E1.
For E2, would the what you call it, the radius be the x component of like E2? Or,
the radius? What do you mean? What do you mean the radius? Like.
So you know how it's like going in like the x direction. So wouldn't you just use the angle to find the x component and then
of E2?
Yeah.
E2 is only in the x direction, so this is the x component, and the y component 0.
Wait, so like, how do you know that E3 and E1 go like to the right and the other one goes to the left?
Because electric field points away from a positive charge, so this one points away.
I keep forgetting that.
Yeah, I forget that a lot too.
Because like I thought that like it depends, but what was if P is positive or? Like,
that's a whole separate thing. The electric field does not depend on what charge is at P. The electric field is just the electric field.
I see.
It exists at a point without anything there. Yeah, go for it.
So then you just points towards -1 because it's a -1, and then you just have to add them together.
Wait, -1. Sorry, what's -1?
There's the negative charge because it's negative, and then it points towards negative charges.
Yeah, this one points this way, right? This one points towards the negative charge, and so the sum of all these three is the electric field at that point.
And like.
Yeah.
And like, what are all these numbers? Are these like just in the x direction, or are they just like magnitudes?
They're just magnitudes. So now we got to figure out the extra. So yeah, now we have to figure out what's the x and y components, right? So let's start with the y components. Honestly, so the y component, what's going in the y direction? Well,
yes, as a number.
Right. We know that this angle is going to be 30 degrees. We also know this angle is also 30 degrees, right? So then what's happening in the y direction? Well, it's going to be E1. Sorry. Well, I'll start with E3 actually. E3 sine theta or sine 30, and then minus E1 sine. That should have been a 3 there. Sine 30. And so you see E1 and E3, first of all, are equal. So this will be 0. I don't even have to calculate anything. EY will be 0. The electric field has a 0 in the y direction because these will cancel each other out, these two vectors. Right? Now in the x direction, we have a more complicated thing happening. So EX is E1 is in the positive x direction, so that's fine. So it's going to be magnitude of E1 times cosine 30 plus magnitude of E3 cosine 30. So these are, again, E3 and E1 are also the same, so I can just put a 2 here, but just write it out fully. And then minus just the magnitude of E2. Just the magnitude of E2, because that's going here in the negative x direction. And this will be our x component. It's also going to be the entire magnitude of our resultant electric field because the y component is 0. Right, so I can simplify this to 2. Well, whatever. I'm not going to simplify to that. So it's just going to be that 16,875 times cosine 30 minus 11,250. So I got here that this is 17,978.36 newtons per coulomb. That is the x component. That's also the entire magnitude of the vector. So magnitude of E is 17,978.36 newtons per coulomb. Which direction does it point in? Well, its x component is positive, so it points that way. Wait, actually, this would, yeah, I'm realizing now, these don't have to be absolute values. And in fact, they shouldn't be absolute values. Although this is an absolute value. Okay, there we go. Now we have it. That's not a vector, that's a component. So there you go. This is a vector. Okay, hopefully that didn't confuse anybody there. That is that. Okay, yeah?
No, it makes sense. I think, and so you just find the components and you just find the magnitude.
Yeah, and from that I find the magnitude, right? You would do to find the magnitude. You do it's the square root of the x component squared plus the y component squared, but this is 0, so it's the square root of x squared, so it's just the x component. Is all that's left for our particular example here. So now we know the magnitude of the electric field. We also know that it points that way. Right? It points that way. So if I were to put a -5 nanocoulomb charge there, this is going to be part B now, what's the force that it would experience? Well, F is equal to Q times the magnitude of the electric field. So that's going to be -5 times 10 to the -9, or it was 5 nanocoulombs, -5 times 10 to the -9, times the magnitude of the electric field. And, well, I guess this doesn't actually have to be negative. I mean, we'll just multiply by the magnitude. And then the direction that it's going to go in is opposite of it. It's going to be negative, right? We're going to get a negative value. So if this was our positive value, then the force is going to go that way because it's a negative charge. So multiplying that together, it's just going to be -5 times 10 to the -9 times 17,978.36. So I get that the force is -8.98918 times 10 to the -5 newtons. And let's see if that's what it is.
So I have a bigger question.
Sure, yeah.
So for part A, when you're calculating E2, why is the radius 0.04?
Let's see. E2.
Because like when I look at the diagram, I would assume that it would be like, like the magnitude, like cos 30. So,
yeah, because you're saying it's a circular arc, I think.
Oh, it's a
So what's your question though? Are you asking like what's the length here? Is that what the question? This blue line?
No, I'm just asking why is it 0.04?
For here, why did I put 0.04 on the bottom here? This one?
Yeah, for E2, yeah.
E2. Well, it's part of the formula here for the electric field. So the electric field is defined as KE Q that's charging Q that's causing the field over R squared, distance from that. So now we got to find that's R here. That's the distance from this charge to that point, and that distance is 4 because this is a circle. This is like a circle here. So if one of the radiuses is 4, then another radius is also 4.
Oh, it's a circle. Oh, okay, never mind. I
Right?
treated it as a triangle. Okay,
Exactly.
Yeah.
It's a circle like that. So it has. Okay. So there's that. That's the correct answer, and correct direction. Everything's good. So that's 19. Any questions about number 19?
These questions seem pretty straightforward. There's not like tricks to them. It's like,
Yeah, some of them are a little. Got to put a little bit of work, but yeah, they're going okay so far.
like they're way easier than the wave ones at least. Because like for the wave ones, like it was a bunch of like, oh, what's B, what's K, and then sometimes you get them messed up because it's like, is B the one beside the X or like omega? I mean, is omega the one the X or the one beside the T's? And it's like, it was much of like remembering, but Very easy. All these seem very easy.
Yo, can you show the answer to part A real quick? Cause I just forgot that.
Part A, the answer's right there.
Wait, hold up. Which one is it? The one right there. Oh, okay. All right. Thank you.
Right there. Is that right too? I didn't even check if that's right, but I know I got the other number right, so this one might be right. I can't even see it. Yeah, 1.8 times 10 to the 4. Yeah.
Oh, 1.8 times 10 to the 4?
Which is this? Which is what this is.
Oh, okay. All right. Yeah, I was tripping for a second.
Yeah.
Thank you.
Okay, that's that. So, okay, then let's move on to number 23. If nobody has any more questions before we keep moving. Okay. Okay. So, I should have discussions open, I realize. So, discussions are open. So, if you want to say something, then there you go. So, this is electric field line section now. So, 3 equal positive charges, Q, are at the corners of an equilateral triangle of side A, as shown in the figure. Assume that the 3 charges together create an electric field. Sketch the field lines in the plane of charges. Well, let's start with that. So, sketch the field lines in the plane. So, you know what, to do this, I'm going to take another screenshot of the question. And just zoom in a little bit.
Yeah, we can take this one because we won't even have any like drawing questions on the exam. Like we can still do it.
That's true, but so I won't spend too much time, but it's good to understand what's happening. So here's our thing. Now, where's the electric field lines going? Electric field lines can only end at a charge, or start or end at a charge, or infinity, right? They can only do one of the two. So electric field lines always go away from positive charges, so it would be going like that. We'd be getting that, I guess. And would it be going like this? No, I think it would curve up like that.
Yeah, we'll do that. We'll do that, and we'll just do that for everything.
Right. So it would go like this. There's the field lines, and then what's happening in the center? What about one that goes in here? Well,
they just curve toward
I think they just curve out like that. Yeah. I think they just curve out like that, and then this.
Maybe if it's like one in the middle, it will like curve in the front like infinitely.
I'm not sure.
There should be no net force in the middle of the triangle, so there has to be no field line in the middle of the triangle.
There's no net force? What about on a...
Yeah. That's only true for some points.
Equilibrium, I think, over there.
That's only true along the, like if you draw a vertical line as the height of the triangle, right? So there's some points, but I don't think it's every point.
Okay, yeah, in general, this is correct. They drew much fewer lines than what I drew. So, but this is we have the right idea. I'll just draw it kind of like how they have it. So, of course, this goes up, 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 and you can kind of imagine it's the same thing for the rest of them, right?
Wait, so I know for what like one question, I think it was in the Weber sign. You have to like count electric field lines. Do you think that's gonna be the case on the exam or not really?
Probably, I don't know. There could be a Gauss's law problem where you have to count field lines, but not sure. Yeah, I don't know.
Can we do one of those then if there's gonna be one?
We'll get to that. Yeah, we're not in Gauss's law section yet. I don't think we're next. The next section I think is Gauss's law. So 23.
So
yeah.
So, just like clarify, why isn't there like a field line inside the triangle? Is it because like there's like an
because right here, imagine I put a positive charge right here. Imagine I put a positive charge. What forces would it feel? Right? What forces would it feel? Or what electric field would it feel? Well, it would feel an electric field going this way, and this way, right? Which would all cancel out, right? Which would all cancel out. It would have a net 0. And then if I put so that was for a positive charge. I mean, I guess I could have done it differently, but so for a positive charge there. And then for a negative charge, I mean, it'll be the same thing, but just oppositely. So it'll be attracted that way, attracted that way, and attracted that way. Those will also all cancel out. So the idea is that there's no net, the net electric field is 0 here. So there should be no field line in the middle. Which is why there's no field line going through the middle. Right? There is no field line that goes like this. Or like this. Or like this. that point where they intersect would have a field of 0, because
0.
right, because the net force there is 0, net field there is 0.
Okay. Yeah, makes sense.
So there's no field line.
So like, how would they look like if it was like one of them was like the top one, for example, was negative? Would they just all curve towards that one?
Yeah. These would still go backwards, I'm pretty sure, but these would all then curve in. Anything that's curving would curve into the negative.
They wouldn't they all curve towards it? It's just like some of them would go off the screen when they curve, but like not all of them.
Yeah, I guess like this one would go like that probably and curve around like that, right? Like. So that's that. Okay, and then the next question is, what location other than infinity is there a net electric field of 0? That's the middle. Like I said, why I explained it. And then what are the magnitude and direction of the electric field at P? Where's P? Right there. Due to the 2 charges at the base. Okay, well, to do that, I'll just put another version of the picture here. So the magnitude and direction. So let's start with drawing out the field line. So this is going to be one electric field like that, E1, and another electric field like that, E2, right? Field vectors. And so those will add together to get a net electric field, and that's going to look up like, it's going to point up like this. So notice the x component is 0. So we already know that EX equals 0. Now EY is going to be, now this is an equilateral triangle, so the angle here is 60 degrees. That means that this angle is 60 degrees, which means that this angle is 30 degrees. Which we don't actually care about. Actually, I was going to use that, but we don't have to. So I'll just use 60 degrees here. So the y component, if I define this as positive, they're both positive. So it's just going to be E2, the magnitude of E2, times sine 60, plus the magnitude of E1 times sine 60.
Sorry, why is it 60 degrees?
Because this is 60 degrees down here, right? Because and that's 60 because it's an equilateral triangle. So an equilateral triangle has all 3 angles are 60 because.
Oh right, 180. Okay, yeah.
All the angles have to add up to 180, right? Yeah. Don't worry. And so then that means that this angle is also 60 up there, right? Yeah. So then we have this. Well, let's figure out what sine of 60 is for both of these. Yeah. Sine of 60 is root 3 over 2. So, well, we'll figure that in a second. What's E2? The magnitude of E2 is going to be KE times the magnitude of Q. So, well, it's just Q over A squared times root 3 over 2 plus exact same value. So it's going to be KEQ over A squared root 3 over 2. So you can just write it as root 3 KEQ over A squared. And that's it. That is the magnitude of, that's it.
Could you have also simplified it like a bit and say like, since E1 and E2 is the same, you just do 2 times that? Or it's not the same?
Yeah, no, it is the same. That would have, I think, been jumping ahead. I did that step right here, pretty much, between these 2 steps. They ended up being the same, so I just added them together. And then, yeah. I didn't do it here because I didn't want to add confusion up here. They are the same, so yes, you could have done
Okay, thank you.
and then the question also needs direction, so it's this up. Or you can write that as, a better way to write that is j hat. Right. And yeah. So 23, I'll just check my answer for 23. 1.7 KQ over A squared. That is root 3 1.7. Yep.
So if we calculate the x direction, would it cancel out?
It would, yeah, it would, because if we do the x direction, it would be the magnitude of E1 magnitude of E2 cosine 60 minus the magnitude of E1 cosine 60, right? Because this is positive x and this is negative x. So since E2 equals E1, this equals 0.
Okay, yeah, yep, that makes sense. Yep.
So, yeah, that's that. Direction of the electric field. Yep, that's it. That's the question. 23 is done. Any questions? Okay. I will take that as a no. So 24 is our next one. So it's motion of a charged particle in a uniform electric field. This is the section we're in. So, a proton accelerates from rest in a uniform electric field of 640 newtons per coulomb. At one later moment, its speed is that many megameters per second. Non-relativistic because v is much less than speed of light. Okay. Find the acceleration of the proton. Over what time interval does the proton reach the speed? How far does it move in its time interval? What is the kinetic energy at the end of it? So, a proton in a uniform electric field is essentially something like kinematics. We're just doing kinematics because the acceleration is just the acceleration is the e vector. Yeah, the acceleration is 640 newtons per coulomb. Is that what the acceleration is? That doesn't make sense. How is newtons per coulomb meters per second? That doesn't make sense. A is not
you can find A from E and the mass of the proton or electron. I don't remember.
Because no.
It's a proton, right? Yeah.
Yeah, it's
so
a proton.
You do MA equals KEQ. Or sorry, MA equals K times the electric field. Like Q times the electric field, because it's a force. You just have to find the acceleration.
Yeah, okay. Sum of the forces equals MA. What's the force? There's only an electric force acting on it. That's equal to MA. What's the electric force? The electric force is K times the electric field. Sorry, Q times the electric field is equal to MA. So if we want to find A, we just divide this by M. So it's Q over M times the electric field. Okay, thank you. Good. Then we just do, we can find that. We can find the acceleration. And then, so let's highlight all the information. Uniform electric field, that's that. At some time later, its speed is that. Find the acceleration of the proton. Well, that's going to be this first step. So what's the charge of a proton? Well, the charge of a proton is E. The mass of a proton is 1.6726 times 10 to the negative 27 kilograms. And that's all we need to know. We know everything else. So acceleration is going to be E times E. Not like, I guess I'll write fully what E is. E is 1.6022 times 10 to the negative 19 times 640 over 1.6726 times 10 to the negative 27. So 1.6022 times 10 to the negative 19 times 640 over 1.6726 times 10 to the negative 27. So I got that the acceleration of the proton is 6.1306 times 10 to the 10 meters per second squared. Let me take a look here of what if that's the answer. This was 24 that I just did, so there's no solutions for it. So I have to look at Slater. Exercise 24 we're doing, I think. Yeah. 6.14 times 10 to the 10 meters per second squared. Good. That is the answer for A. So B now. Over what time interval does the proton reach this speed? So we just need to use our kinematics equations, which I don't think I have here, because this is the wrong sheet. I do have it.
Wouldn't it be VF equals to VI plus A times T.
Do we know VI from
Yeah,
rest?
because it just starts from rest. Yeah.
So VF equals What's the question? What was the question? Over what time? Yeah. So VF equals VI. VI, if I can spell. Plus AT. I'll say delta T. We know that this is 0. So essentially we know that delta T equals VF divided by A. Magnitude of A. Right? I guess magnitude of VF is also important. We know it's in the same direction, though. So it doesn't matter. So now VF is 1.2 meganewtons. That's times 10 to the 6? I don't know what it is. Is it times 10 to the 6? Meganewtons?
Yep.
Yeah, okay. Thank you. Over 6.1306 times 10 to the 10. So 1.2 times 10 to the 6 over... yeah?
I think the V final is supposed to be squared.
Is it?
It is V final square equal V initial square plus 80. Acceleration times time.
Oh, I think that's a different.
I think you're mixing up two formulas there. You're mixing up two formulas. I have the formulas here too. VF equals VI plus AT. There's also VF squared equals VI squared plus 2A delta X. That might be
I think that.
Mixed up these two. Yeah.
I think so, yeah.
So that's fine. And then let's look at, this was 1.95. Yeah, I just missed the times 10. I don't know, I didn't write it. Times 10 to the negative 5 seconds. Good. That worked. So good. That's the delta T. And then how far does it move in this time interval? Well, we need delta X. So to find delta X, we do delta X is equal to VIT plus 1/2 AT squared. So this is just going to be, well, VIT is 0. And it's just going to be 1/2 A, which was 6.14 times 10 to the 10, times 1.957 times 10 to the negative 5.
Was it 6.13?
Yeah, you're right. 1, 3. And then we just do this. So 0.5 times 6.13 times 10 to the 10 times answer squared. So I got 11.743 meters, presumably. Yeah, meters, I guess. Meters. There you go. I should do some unit analysis on this, but yeah, it's fine. It'll be meters. Okay, then that's that question. And then what is the kinetic energy at the end of the interval? This isn't too bad. So part D is just what's the kinetic energy? Well, to do that, you just have to remember that kinetic energy is 1/2 mv squared. So 1/2 mass of a proton. Well, the mass of a proton is 1.6726 times 10 to the negative 27. And the final velocity was 1.2 times 10 to the 6 squared. Right? So the final velocity was 1.2 megameters per second. So it's going to be 0.5 times 1.6726 times 10 to the negative 27 times something squared. That something is 1.2 times 10 to the 6. So this is 1.2 times 10 to the negative 15 joules. And there's all the answers. So any questions about this one? Okay, then I will move on.
One thing about this is that F equals MA equals FE. You need that to do other kinematics questions as well. Anytime there's a constant E field and they're like asking you for how far does it move or something, you have to. It's the A is not E. A and E are different things. You actually have to find A first.
Yeah. So important equation. There you go. That should be there. Let's see if it's even on the formula sheet. If it says like, probably not because
so.
it's a little. It's a
So.
bunch of
It's
things
just...
combined. Yeah, I understand why, but just out of curiosity, see. Yeah, no, there's a bunch of formulas here though. That's good. Okay, so that's 24. Next is 25. So we have. So a proton moves at that speed in the horizontal direction. It enters a uniform vertical field with a magnitude of that. Ignoring any gravitational effects, find the time interval required for the proton to travel that many centimeters horizontally. So what do we know? Well, we know VI. Come on. There we go. We know VI is 4.5 times 10 to the 5 meters per second. We know that the magnitude of the electric field is 9.6 times 10 to the 3 newtons per coulomb. So we got to find a bunch of other things. So first of all, we got to find what the acceleration is. So what we're going to do is that the sum of the forces is equal to ma. So what's the only force? Well, the only force is the electric force, right? So electric force is Q magnitude of the electric field, right, times ma. I mean equals ma. So then the acceleration is Q E over m.
Wait, didn't we already calculate this? So can we just use
for a proton, it was in a different electric field though.
Oh, it's different, yeah.
So yeah. So now I need the charge of a proton. Charge of a proton is 1.6, that's a 9, 1.6022 times 10 to the negative 19 times the electric field, which was 9.6 times 10 to the 3, and then divide that by the mass of a proton. And the mass of a proton is 1.6726 times 10 to the negative 27. So I got that my acceleration was 9.1959 times 10 to the 11 meters per second. We know our acceleration, so now the question is what time interval is required for a proton to travel delta x equals 0.05 meters. So I just use my kinematics equations again. So we'll have, I know delta x, which is important. I need something with t in it. I know delta x, I know vi, I know the acceleration, so I'm going to use the first one. The first equation. I don't know vf, right? I don't know vf. Yeah, I don't know vf. So I'm going to have to do the quadratic one, I'm pretty sure. So delta, which is delta x equals VIT plus AT squared.
Couldn't you just do 1 over 2 AT squared?
Oh, it should be 1 over 2 AT squared. But VI isn't 0.
Wait, what's VI?
VI, this should be 1 over 2 actually. VI is 4.5 times 10 to the 5.
Oh, okay. Sorry.
It comes in. So yeah.
Yo, what did you use for Q?
Q was 1.6022 times 10 to the negative 19.
Alright.
I'm not sure if the question is asking for the x, like the x movement instead of the whole movement to travel. Oh yeah, horizontally. Oh yeah.
It's in the horizontal direction, right? It moves in the. It's all in the horizontal direction. Yeah. They would have to specify more information there if it wasn't like that.
That would mean that the acceleration isn't applying to this though, right?
If what? If this wasn't in the horizontal direction?
The acceleration would only be vertical. It's basically acting like a sort of similar to how gravity works, where it only acts down.
Yeah. Yeah, it acts. Yeah,
but there's no acceleration in the x direction since the electric field is vertical. So.
Yeah.
Is that right?
Oh yeah, hold on.
Yes.
Proton moves.
And that's what I was trying to say. I'm like, if it's moving horizontally, and the electric field's straight down.
So the initial, yeah,
it's moving
initial
at this.
is Vx.
So then how did we answer this question up here? Proton accelerates from rest in a uniform electric field. Oh, because it's from rest. Okay. We don't
Yeah,
know which
that one
direction. We just
does
know it's
change.
moving. Yeah, we just
Yeah.
know it's moving in the direction. Okay, so from here, okay, that makes sense. Required for the proton to travel 5 centimeters horizontally. Well, yeah, it's actually not. It's delta x vi.
Like this whole
Acceleration
process
0.
is good for y, for the movement of y, and in the y direction, but not for the x.
Yeah, so this is just
It's
0.
just like a projectile motion.
Yeah. So vi. Sorry, we're looking for t. So t is going to be delta x over vi.
Yeah, exactly. Yeah.
Right? So 0.05 over. Okay, sounds good. 4.5 times 10 to the 3, was it? 10 to the 5. So 0.05 divided by 4.5 times 10 to the 5. So I got 1.11 times 10 to the negative 7. Let's check that. Yeah.
The PCS 211 flashbacks are real, man. It's like more like PTSD.
Yes, I agree. So there's our 1.11 times 10 to the negative 7. And yeah, that's the right answer. Any questions about this? So acceleration in the x direction is 0. This is a vertical electric field.
Okay, so it's 0 because it's moving horizontal, right?
Yeah.
So then, if it was moving vertical, it would be like the acceleration that we calculated.
I'm
before.
about to do that. Part B. That's exactly what
Oh,
I'm about
that's
to go
part
into. Part B is what is its vertical displacement during the time interval which it travels 5 centimeters horizontally. Right? So we know this is how long. This is in seconds. Whoop. We know this is in seconds. That's how long it takes to do that. So part B is asking, what is delta y? Right? Delta y. Well, we know that we have a formula. So delta y is VIYT plus 1/2 AT squared. AYT squared, I should be clear. VIY is 0. 0, not null. And delta y is just going to be 1/2 AYT squared. Just take the magnitude. We just need the magnet. We just care about the displacement, so it doesn't matter. And so then here it will just be 1/2 0.5 times the acceleration, which was 9.1959 times 10 to the 11 times t squared. T is 1.11 times 10 to the negative 7. So I got that delta y is 5.665 times 10 to the negative 3. Yeah.
Is that meters or is that
meters? Yeah.
Okay.
Meters. And there you go. That's part B. So there's the answer there. And now for part C. Part C was asking the horizontal and vertical components of its velocity after it has traveled that much. So VFX and VYX is what we're looking for. So let's start with VFX. So VFX is VIX plus AXT. Well, this is 0. So VFX equals VIX equals 4.5 times 10 to the 5. Meters per second. Okay. VFY equals VIY plus AYT squared. No, not squared, sorry, just AYT. This is 0. This is 0 this time. So VFY is just AYT, which is AY was AY was 9.1959 times 10 to the 11 times delta t, which was 1.11 times 10 to the negative 7. So I got that VFY was 102. Well, I guess I'll do it in. So 1.021 times 10 to the 5 times 10 to the 5 times 10 to the 5. Okay. meters per second. Let's check that. 102. That's fine. And 450. Yeah, that's fine. We're good. Everything is good. C is correct.
I would expect one of these a question similar to this on the exam.
Me too.
Just because it's like the long enough question that they could do that.
Yeah, I agree. They would probably a question like this would probably be on the exam. If you ask me. Okay, so let's take a look now at question what? 33.
What did you sorry, what did you get for part B? Just...
Here.
Okay, yeah, I've got the same thing. All right, we're good.
Good. Okay. So 33 is next. I have to take it in 2 pictures. Are we doing 34 as well? No, it doesn't ask us to do 34 in this homework. So 33 is, I made it a little bit too big. And there's our picture. So, okay. Nice. Okay, I can't make it nice. So there we go. That's our picture. So a charged cork ball of mass 1 gram is suspended on a light string in the presence of a uniform electric field as shown in this figure. When the electric field has a strength of that, the ball is in equilibrium at that angle. Find the charge of the ball and the tension of the string. Okay. Not bad. This is, I think Springer did this one in the study hall, if I'm not mistaken, or something similar. So it's not bad. It's not a bad, yeah, let's just give it a try. So what's happening to this ball right here? Well, it has a few forces acting on it. It's a positive charge, so the force is acting in the same direction. The electric force, I should say, is acting in the same direction as the electric field. It has a force of tension here, and a force of gravity. Right? Those are our 3 forces acting on it. So we know it says it's at equilibrium. So the sum of the forces equals 0. Right? So we got to separate this into the x and y components. So the sum of the forces in the x direction is equal to 0. So what are the forces in the x direction? What are our angles, first of all? Let's figure out our angles. So there's our horizontal. This angle right here is going to be, well, actually, that's not the angle we particularly care about. It's easier if we choose this angle. And this angle is theta. Yep. And this angle,
I don't think we need to use angles. We have the components over there.
Sure, yeah, that's fine, I guess. We have the components of this, so we know the x and y components already. Yeah, you're right. So we don't actually care about. I could figure out the angle, but I don't need to, because
it's given.
Yeah, it's given. Yeah. So some of the forces in the x direction, well, that was positive. So the positive component of the electric force is going to be 3 times 10. Well, I'll just say I'll put the numbers. 3 times 10 to the. No, I'm not going to put the numbers. FEX. And then it's going to be minus the force of tension sine theta equals 0. And what are we looking for? Find the charge on the ball. Yeah, find the charge on the ball. So what I'm going to have to do, find the force of tension. Find the charge on the ball. So somehow I have to say, okay, well, I know Fe equals Q magnitude of the electric field. Oh, yeah, sorry. I don't know the x component of the force. I know the x component of the field. So I know that the force is going to be in the same direction as it, so I don't need the angle there. But I do need, this is not right. What that's going to be is that's going to be QEX
That's it. I think that's it.
You think that's it?
Yeah, like gravity is in the y direction. That's just tension and the electric field.
Is this right? QEX like that? That's the x component.
Yeah, because like you have the what you call it, force of tension in the X, and then you have EX, so you can just find the
Okay.
charge in the X.
For some reason this doesn't seem almost like full to me. I feel like I have to have a sine or a cos theta here, but because I already take the X component
No,
of that.
because you get it in components.
Okay.
So
Yeah,
it's already
charging
broken down into its horizontal and vertical components. You can find an angle if you want.
Yeah, but I guess I don't have to. Okay, so I'll go with that. That's our first equation. Notice there's two unknowns, Q and Ft. So those are the two things we need to solve, so that's fine. Then I need to do the sum of the forces in the y direction equals 0. So what are the sum of the forces in the y direction? Well, I have a couple more. So it's going to be Q magnitude of EY plus Ft cosine theta minus mg equals 0. Okay, and what am I missing? Well, I have a Q and an Ft. So in both cases, I have a two equations, two unknowns. So I mean, like in both cases, I have two unknowns. So two equations, two unknowns. I can solve this. So I will do that by rearranging this one into Ft equals QEX over sine theta, and subbing that into here. So then that's going to be QEY plus QEX over sine theta cos theta minus mg equals 0, and just solving for Q. So this is going to be Q equals mg over EY plus EX cotan theta. Looks like to me. Hopefully, can someone confirm that is right?
That would be over tan theta.
Sine over cos is tan theta. Cos over sine is cotan theta.
Right, but you have cotan in the denominator, but it should be in the numerator if you're going to do it that way.
No, it's right. I think it's right.
Because I'm dividing.
You can put. Oh no, you can't because it's 1 plus something. Never mind.
Yeah, exactly. Yeah, I think you just.
I think it's correct. It is correct.
This is right because like this will combine into cotan, and then that will go. That quantity will go in the denominator.
Right. Okay, that makes sense.
Yeah. Okay, so then Q is equal to, let's start. So 0.001 is 1 gram. Sorry, is 1 gram. 0.001 kilograms is 1 gram. Times 9.81 divided by the y component, I thought that was the g component, the y component of the electric field, which is 5 times 10 to the 5. Plus the x component, which is 3 times 10 to the 5, times cotan theta, which is 1 over tan theta, and theta is 37. Pretty sure I'm in degrees. Yeah, I was in degrees the whole time. Okay, that's fine. So Q is 1.09228 times 10 to the negative 8 coulombs. Let's take a look if that is correct. 33, 1.09 times 10 to the negative 8 is correct, yep. So that's part A. And then part B is just going to be solve for Ft here. So Ft is going to be this answer that we just got times the x component, which was 3 times 10 to the 5, over sine theta. And the sine theta was 37? Yeah, 37. So Ft was 5.445 times 10 to the negative 3. My answer for that. So, okay. Any questions about this? Any questions about this one? That's 33. Okay, 48 is next.
Yo, could I see the final answer real quick?
Yeah, 48's right there. I mean, the answer's right there.
Alright, thanks.
No problem. 33 is done, so 48 is here. So this is one of the challenge problems, so we don't have to stress too much about it. This is the end of chapter 22, the last question in chapter 22, which is electric fields. Next one's Gauss's law after this. Oops, I lost the page. So, let's see. 8 charged particles, each of magnitude q, are located on the corners of a cube of edge S as shown in this figure. Determine x, y, z components of the total force exerted by the other charges on the charge located at point A. Okay. What are the magnitude and directions of this total force? Well, that's not hard to find after, so it's the hard part is part A. So, okay. Well, yeah, this is going to be a second. So let's see. I have a lot of forces acting on it here. I have 1, 2, 3, 4, 5, 6, 7 extra forces, because there's 8, of course. So I have 7 forces acting on this point right there. Maybe, let's see, do any cancel? No, none of them cancel. They're all repulsive, so they're all going away. Yeah, nothing cancels. No, does something cancel? No, nothing cancels.
Nothing would cancel, and I would highly suggest we use components for this because this is going to get very long.
Yeah, use components like
do all the X components, all the Y components, and all the Z components,
yeah, okay.
And then you get the total from that. Because doing it with like all together would be tough.
Yeah, fair enough. So the X component, let's start.
I would say it's impossible.
Yeah.
I would say it is impossible to do them all at the same time.
Yeah. No, you can get angles for it. I think you could probably find each angle that points towards the point A.
Would it be 45 degrees? Because it's a cube. They're all magnets.
Yeah, but the tricky one's going to be the diagonals.
Oh, that's true. Yeah.
It's still 45 degrees. It's just 45 degrees not in the X or Y direction.
Yeah, exactly.
45 degrees. I forget what that was called. We did that 211, where you found that thing.
They're called coordinate direction angles. That's what they're called.
Yeah, something like that.
Alpha, beta, gamma. Yeah. So the X components. Let's see. Okay, well this is the X direction. So what's affecting it in the X direction? This isn't affecting in the X direction. This isn't affecting in the X direction, and this is also not affecting in the X direction. So what we have to figure out is the X value, X effect of these 4. Right? So the force, are we looking at the force? The total force exerted. So I'm just going to have to add up, so the sum of the forces is, well, the force shared by each of these. So it's going to be KE, Q1, Q2, they're all the same charge though, so it's going to be Q squared over, let's just start with this bottom one, I guess. So I just take the X distance. I guess I just take the X distance, so it's going to be S squared. I think so. They're all going to be that. So this is going to be 3 times that.
Four times that, because there's four particles.
4 times that. Is that right?
Yep, that's just for the X.
Say one more time why those 3 don't have X components again.
Well, because imagine like here, what magnetic field, what electric field is being caused by this point, this charge right here? Well, it's pointing in this direction, right?
Mm-hmm.
That has no X component. Then the one caused by this is going like this, no X component either, and the one that this is going up like that, no X component either.
Okay, I see.
Right.
Thank you.
Okay, so that's for Y. Then that's for X. So now for Y, well, the sum of the forces of the X direction.
Isn't it going to be the exact same thing?
Yeah. Looks right. Looks like that to me.
And sorry, could you explain why is it times 4? Is it because there's like 4 charges on like one?
Yeah, there's
plane?
4. So like for here for the x, so for the y direction one, right? I'm looking at the electric field at this point. So what's contributing to that motion in the y direction, or the vector in the y direction? Well, these ones are not contributing anything in the y direction. These ones are each contributing a force just in the x direction, or just in the y direction, of KEQ times, so KE Q1, Q2, but they're both Q's, right? Over the radius squared. But just in the extra, is that, am I doing this right? Is it just, I just consider in the extra, is this going to give me the right answer if I do it like this?
Yeah, that's
I
what
don't
I'm.
think I don't think
go
so
ahead.
because sorry. You can go ahead.
Oh, me?
Yep.
I'm not. It makes sound sense what we're doing now, but I'm not sure if this would work. This definitely works for obviously the top right corner, and
Yeah.
I'm pretty sure it works for the bottom right corner as well. Although I'm not 100% sure, because if you were to find the actual radial distance, it's
Yep.
√2.
Yeah, I agree.
And the distance from the one from the very
But
center, like at
no, but
what is zero,
finding
it's gonna be farther.
magnitude and angle. That's finding magnitude and angle. That's not. If you were to make it into a component, you'd have an x component and a y component. They would also be s, which is why I'm
Exactly.
questioning myself.
Like
the
we
x
can get
component
just...
of that is s. Yeah, go for it.
Yeah, exactly. We can just get the individual x, y, z, and then do the whole Pythagorean to get the magnitude, and then we can do the weird like cos sketchy stuff to get the direction.
We just want to make sure we're getting these right. I mean, let's see. I mean, are we getting these right? I can look at the.
Yeah, that should be correct, because you had √2 of a radius, and then you did cos 45 degrees. You end up with 1 again. So
that's what I'm thinking, right? So it would be. Let's see, where are we?
They might only list the final answer, like the final magnitude.
No, they give fx equals fy equals fz equals 1.9 keq squared over s squared.
So we are doing the correct way then. We would end up with.
But 1.9. 1.9.
Oh, this is 1.9, not 4?
Not 4.
I think they're
for the individual x, y, z directions. It's
how would it be less?
Yeah, that's doesn't make any sense.
I think
it'll be less because s is squared and the distance they vary. Like they're not the same and they are greater. Like the closest one is gonna be just the one that is like just perpendicular to it, like closer. But the other 3 are gonna be far away from there. And the thing is that s is gonna be squared, so the distance will be like affect even more.
I'm assuming the answer's in terms of s though, right?
In terms of s, yeah, in terms of s.
So then I don't think that would make a difference, and we're only considering the x position, like when we're looking at the x direction of the forces, and then the y position with respect to a, for the y direction of the forces, right?
I think that's what we're doing, but they're doing the same thing. Well, no, they're doing something more complicated. Actually, they're not doing the same thing. They're doing something quite a bit more complicated.
I think the magnitude should be the same because like it is symmetric, so it will be the same everywhere. But probably the values are going to be different because of the distances.
Yeah, this value here is going to be different because the distance is there. I think that's right. So we have to take this into account, like take different things into account here. So
does Slater show a breakdown of how they did it?
Yeah.
Did they use components?
They used components. They used like the unit vector. Yeah. And
I was doing the homework and I looked at this question and I looked at the Slater's answers. It was like so confusing. Like they didn't make sense to me.
It's pretty complicated. It is pretty complicated. So
if we start like trying to find the forces one by one and then we add everything.
Yeah, I'll just go through the Slater solution, and then like I'll do it here manually, and then we'll see how that goes.
So I have like a question.
Sure.
So like you know how like some of them are like diagonal, when you're going to like that red dot that you drew.
Yeah.
So wouldn't that not be 4? Wouldn't that be like less or like more than 4? I'm just
What would be 4? The distance?
Yeah, wouldn't it not be 4?
We don't know the distance. Distance is s, right? Distance is just some s. The 4 was coming from the fact that we had 4 charges doing
4
the same
charges.
thing. But I guess you can't just take the x component of the direction. You have to take. That's not the same thing as taking the x component of the force. So,
Honestly, in terms, because it's a cube, we know, like, okay, if we're looking at the point that it's asking, the x components and the y components should turn into like a diagonal component, because they should be, if they're equidistant from the point, you end up with your force should be pointing like directly in the xy like sort of linear direction. I don't know if that has something to do with why they wrote 1.92, because then you get a triangle. You get your x component, like if you, I don't know how to draw that. You have like E coming from here. No, from like, so that's the charge in question, and then there's the charge to the top right of it, and then the force or the field from that charge, or I guess the force as well, because they're all positive, is going to be pointing like in the x direction.
Yeah.
And then the charge opposite or diagonal from that top right corner is the top left one, and then that's another triangle. Like you can, or not a triangle. It's a, what do you call it? Like what is it? You can the total. Yeah, it'll be in the middle. That's what I was trying to say.
Yeah. Including this one though, as well, right? This one will also be that direction.
Like it's a triangle. It doesn't look very much like a triangle from there, but it's like a triangle pointing in that XY direction.
Yeah. But, and then we'd technically be able to do that for each of the planes.
And they're all gonna be the same. Like we just have to do it once, and then we can know all of them because they're all the same.
Yeah. Okay, so then let's try that then. Yeah. What would the resulting force in the XY plane would be, would be Q times, well, okay, whatever. It's Q times the field, but that's not what we're doing. So the force would be the force because of this one, plus the force because of this one, plus the force because of this one. Right? And that would be in the XY plane.
Yes, and that's gonna be complete like 45 degrees from the vertex.
Yeah.
Right? Because the other two cancel. So you just add the one component of the one component of the other, and then the full component of the one that is opposite, like completely opposite, right?
Yeah, here. I gotta get this radius. This is root 2s. Is that what it's gonna be?
Yeah.
Root 2s. Okay.
Or s root. Yeah, root 2s. Yeah.
Okay. This should be squared, and this should be squared. So then this is gonna be 2. Yeah, this is gonna be 2 KEQ. Well, I'll factor out the KEQ squared. So KEQ squared over s squared times 2 plus 1/2. Yep. So 2 plus 1/2 is 3.5, which is 7 halves, I think. 7 halves, is that what it is? 2.5? Yeah. No, 2.5. 5 halves. Never mind. What am I talking about? 5. So 2 is 5 halves. So 5 over 2. That's an s. That's an s, and that's a 5. You know what? I'll just leave it as 2.5 because we're in decimal. That's fine. Okay, still not right though. The problem is there is a problem. That this, not that this isn't right actually. Sorry, not that this isn't right. Actually, I see what we're gonna do. This is the 2.5. This is the component in this direction. But we want to know what the actual x component is. So we need to do cosine 45.
Wait, it's you said the answer was 1.91 or 1.92.
Wait.
Yeah, 1.9.
It's root 2 plus 1/2.
root 2
If
plus
it's 1
1/2.
point, if it's 1.91 or 1.92, like root 2 plus 1/2 is 1.914.
It's just 1.90 is what they give here for some reason.
Oh, then I don't know if that would be correct or not.
Or in somewhere else they give 1.93.
Because if it's if we're looking for the magnitude in the xy plane, the 2 ke q squared over s squared would actually be root 2, because you would find that's the magnitude of the x component and the y component, and then you'd find the xy component by doing the square root of
true.
x component plus y component squared.
Because you're doing
Like you get
cosine 45 this times this?
Like you see on your drawing, you have 3 green arrows, and then you have the leftmost arrow and the rightmost arrow. Those have the same magnitude because they're the same distance away from the same point. And if you were to find if you were to combine those 2 vectors into one vector that points in the xy plane, because they have the same magnitude, it's like a 1-1 triangle. Like it's a 45-degree triangle. So you end up getting root 2, and then because you just combine root 2 plus 1/2 keq squared over s squared, you get.
But where's root 2? This is 1 root 2 like this?
It should be the same, because you get there are the the x component and the y component are the same magnitude.
Yeah.
So you get root 2 times whatever the side length is.
Adam, take the green vector pointing in the positive x direction.
Yeah.
Can you move them?
Oh, I think I see what's happening here. That's the y. That's the thing.
We're making a triangle.
Okay.
Yeah.
Okay,
So
now I understand.
Because the x and the y components are the same magnitude, you have a special triangle, which means it's root 2 times your magnitude of the side length.
Yes. Okay.
And then
so,
you get.
And so this would be root 2. Okay, this would be root 2 there, and then I would just have. This is right. This looks right.
Yeah, that doesn't change.
So this is just root 2 plus 1/2. So root 2 plus 1/2 0.5 is 1.91. So this is 1.91 keq squared over s squared. So that is the. Let me think about that for a second. That's the component.
But that's only on the XY plane, right? You have what about the other chargers there?
They'd be exactly the same.
But the one that would be true, but the one that's confusing me is the one that's completely diagonally opposed to point A.
Yeah,
so the one that's sitting in the origin.
In the origin, yeah.
No, but that's because it's not in a straight direction. It's but it points in the XY plane.
Yeah,
so
hold
you
on.
just add it?
No. There's more happening here. Wait a second. In the XY plane, these also have components in the XY plane, though.
Yes, all of them. I think the only one that doesn't have is just the one on the very left corner.
Yeah.
Like the one is in the x and in the x-axis. I think that's the only one that doesn't have x component.
Yeah.
Oh, and the one below it, but the others, all the rest have.
Okay.
I feel like there's a reason this is a challenge question.
There's a reason. Let's take our 20-minute break. I'll read the Slater solution over the 20-minute break and see what's gonna happen there. I don't know. I'll read it over. I'll try to make sense of it, and I hope maybe other people try to think about it too over the break. And then so we'll be back in 20 minutes to continue. We'll be finished. We're done chapter 22 after this question. We'll move on to chapter 23. We can probably get a good few questions done in chapter 23. There's only 5 questions, so possibly we'll be able to finish 23. Not necessarily, though. And then, we still got a lot of work to do after that, so we'll have lots of work the next 2 days. But okay, so 20-minute break now, guys. I'll read the Slater solution for this on the break. So, okay. Talk to you guys in 20 minutes.
It seems we have found a spooky coincidence, guys. We thought we had the answer, but we were wrong.
Yeah, that's true.
Well, the question is very, very hard.
Yeah, the question has it's not something we're gonna be doing in class. So.
No way. There is no way that they will give us a question like this on the exam.
We say so confidently.
Come on, like you saw their questions, like they're.
No, they
At
wouldn't
some
do that.
point-
They wouldn't do that.
Famous last words
Yeah.
before
At
disaster.
some point, they're like just high school questions. Like I swear, the wave one, I swear it was on my high school midterm, like in my high school unit test.
They could ask you what would be the direction of the net. Like
I'm
they
glad they
wouldn't
don't.
ask you to do the calculation itself, but they could say like, what would be the direction or something. You could say like it's up, it's upwards in the positive XY plane or whatever.
Yeah, they could do that. Yeah, I can see that.
No, I'd say you're most likely. I mean, if it's going to be for electricity, you're most likely going to be asked a question on kinematics.
Yeah, those
because
kinematic ones. Yeah.
it requires you to. Well, it doesn't have a lot to do with electricity, I suppose. It has one thing to do with electricity, and then that's it.
Are you guys studying for the past chapters? I'm just gonna read them over before the test.
I was doing the old tutorials because there are a good variety
Yeah.
of questions on older material.
Oh, you're going to the self-assessment and website?
No.
The quizzes that are on the website, like the tutorials.
Yeah,
that
I
you
know what
used
it
to
is.
do.
I don't do. I was just doing the tutorials in the D12.
Oh, okay, I see that. That's
Yeah, those
fine.
ones are pretty good, and all the answers are posted and stuff. So
Well, only the numerical. Well, that's what they say.
yeah, the older stuff isn't as conceptually difficult. At least I don't think anyway. I guess it's different for everyone.
Oh wait, you have the actual worked solutions for the tutorials.
I have the worked solutions. No.
Oh, okay. Never mind. That's
No. I mean, I have the work solutions in the sense that I worked them out, but I don't have the work solutions like ones that they provided.
Oh, okay. Yeah. Okay.
What page was that? This question that we were doing now, the cube one. I forget which page it was.
What page it was?
Yeah.
I don't
614.
know what page it was. It's the last question.
Chapter 22, right?
Yeah, the last question in chapter 22. No, the one thing I would suggest studying up on, if you had to study something for the exam, would be standing waves, because standing waves can be like kind of difficult to figure out some stuff for them. And like what was it? Like nodes and antinodes, and like open loop, open-ended, close-ended, stuff like that.
Oh yeah.
That can get quite confusing.
You know what? I think they posted that. Didn't they post the answer for the midterm?
You can look at your midterm and see what you got right and wrong, and like what the actual answer is.
Yeah, I probably will do that. I will just look over the midterms.
Okay, I guess that's fine.
Like there are only 7 questions coming from that part. Like I don't think they will bring like that hard concepts one. I don't think so. It's my.
You should always expect to be evaluated. Expect to be evaluated at least once on every topic that you went over.
Yeah, the main topics. The main topics, not the side ones. That's anything.
Yeah, I would say being the hardest class to study for is, I guess, the CPS one, because there's no direct, easy way to study for it. You kind of have to
Well, I
like
did
learn
the
the
midterm
material.
that they post. I did the final. They posted a practice final exam. Like my professor noted in the common one. and
They
it's pretty
posted a
easy.
practice final.
Yeah, I can send it if you want to. It's like my
practice
professor
final,
posted. Yeah.
oh, it's like
A
just
final.
your professor did it.
Yeah.
Oh, okay.
So it's like a final exam she did for us to practice.
Okay. Yeah, if you want to send that to me, that's good. I'll use that.
Okay, I will send it to the CPS discussion.
Don't send the D2L link. You'll have to send the
Yeah, PDF.
yeah.
I know, like you don't have access there.
Maybe. I don't know. Send it.
CPS discussion.
Can you please go?
Okay, can you see it? I just sent it.
In the CPS discussions. Is this what I think it is? Is this the one that I already? 1 second. Oh no, it's different. Okay, never mind. I thought this was one I already got from someone else. Okay. Yeah.
Just open it with docs and make everything black if you don't want to see the answers. That's what I did.
Okay. That sounds like a good idea. Download it then.
Okay, hi everybody. I am back. A few minutes late, but I am back. There we go. There I am. So yeah, let's I guess keep going. Did everybody make it back? Anybody who's we're here.
Okay. Yeah, Adam.
Hi, fine. How's it going?
How much longer are we continuing this for?
For until 9.
Okay.
Until 9. Yeah.
Alright, sick.
Okay. So, yeah, let's keep moving on this problem. So, I read the Slater solution for this problem. Let's see, where are we? We're at 3 hours. Yeah, okay. I read the Slater solution for this problem, and a good amount of it makes sense, honestly. But there's a specific part that doesn't make sense. So maybe if someone could tell me what they think about it. Let's see. Okay, so I'll erase everything that we have here. So, there. So to figure out what they do is they first find the electric. I mean, it makes sense to find the net electric field and then multiply it by Q to get the net electric force, which is essentially the same thing as what we're doing. It's just that you just have to deal with one Q at a time. So it's the same thing. It's just a little tiny bit simpler to write. So the sum, like this. Okay, first of all, we have to name all these points. So that's point A. This is point B. This is point B, A, B, C, D, and this is point E. So A, B, C, D. Oh, that doesn't make sense. A, B, C, D, E. I don't know what letters they use here. This looks like this is going to be C, F, and H. And then this is finally G over here. I'm pretty sure. Maybe I messed that up a little bit, but that's the lettering that they use in the solution. That's an E here. And that's point A, of course, right there. So to figure out, there's 3 different kinds of complications we have here with the electric fields. We have these 3. We have then, those 3. We have then these 3, right? And then finally we have the last complication, which is these 2, right? This one pair right here. So we're going to take each step separately. So first we're going to deal with the electric field caused by B, the electric field caused by D, and the electric field caused by E. Okay, those are the 3 first electric fields we're going to deal with. Well, those aren't too hard to figure out. Those electric fields are all equal to, well, not all equal to the same thing, so just to be clear here. So electric field caused by B, let's look at B first, is going to be KEQ over S squared, sure. In what direction, though? In the positive Y direction, so that's J hat. The electric field from point D is going to be KEQ over S squared in the positive X direction, so that's I hat, that's an I. And then E is going to be KEQ over S squared K hat. Positive K direction. Positive Z direction, I mean. Okay, there's our first 3. So we know the electric fields from those 3. Now let's do the next more complicated one, which was the electric field from C, H, and F. So this is part 1. Part 2 is the electric field from C, the electric field from H, and the electric field from F. So to do that, let's find the electric field from C. So that's going to be, well, we know that this is root 2s, right? So since we know that that's root 2s, so from C it's going to be EC is going to be cosine
is the G like the bottom left? Yeah, okay.
Not like here, this one.
Yeah, just at the very top. Okay.
At the origin, yeah. G is the
I have a suggestion, and is what if like it will be good if we just work with one direction, let's say just X, and we can see that the only thing that is like pointing towards X is gonna be C, D, H, and G. So we just have 4
That's
points
what we did
instead of
originally. We did that originally, and that we didn't get the answer like that. We didn't get the answer like that because it's a little bit more complicated because of the distances here, right? Because if we just take the X component of this, if we just take the X component, like so, if you're saying like these are not contributing in the X direction or in the Y direction, they're not contributing in the Y direction.
Yeah.
Or no, and they're not contributing in the X direction.
No,
X direction.
they're not. Yeah, and the X. But for example, for Q, it's gonna be just like the magnitude is gonna be just the formula, and the distance is gonna be just the radial distance from there to there. So that's the only difference.
Yeah, it's gonna be we're gonna have this distance, which is different than this
Oh.
distance, which is the same as this distance, which is different than this distance.
Yes.
Right. So there's
Yeah.
Probably would work. Although I think this is just as complicated now as what I'm doing now.
Okay. All right.
Just
Yeah,
in
no,
kind of a
no.
different order. But yeah,
Sure.
that's essentially the same.
Okay.
Yeah.
Okay.
Okay, so then that was like that. Okay, so then I'll get rid of these X's. So now to figure out EC, the electric field coming from C, I need to split this up into the I hat component and the J hat component, right? It's going to be something I hat, something J hat. So what in each? Well, both of them are going to have KEQ over, KEQ over 2s squared. Or I'll be more clear, root 2s squared. So as a s, not a 5, s. Root 2s squared, right? Because that's what this length is. Okay, but which one's in the x direction? Which one's in the y direction? There's nothing in the z direction from this, because you can kind of just look at the geometry of it, right? There's nothing in the z direction that this doesn't contribute anything in the z direction of the electric field. So it's just going to be cosine 45. Similarly here, because we want the x component, so if this is our 45, or I guess this is our 45, it doesn't really matter. Cosine 45. So then we get here, I'm going to get the same thing, KEQ over root 2s squared sine 45. And I'm good with this. I think this makes sense to me, pretty much. So I can simplify this to be, I can simplify this to be 0. So cosine 45 in decimal. I understand it's root 2 over 2, but is that cosine? No, that doesn't make sense. Hold on. Cosine 45 is that 0.7. Wait a second. That doesn't make sense. Hold on. Just see one thing they did here. Yeah, they just didn't write it properly for some reason. Yeah, there's a bunch of typos in this solution, so that's why I'm a little bit confused, but it's okay. Yeah, they just made a typo. So this is going to be equivalently, somehow, 0.353 for 2. 0.353 times 2 is 0.353 times 2 is 706. Oh yeah, okay, that makes sense actually. So what we're going to get, okay, cosine 45 is root 2 over 2. I'll just write that as a decimal, right? Cosine and sine 45 are the same thing. So this is just going to be, K is going to be 0.707. That's root 2 over 2. KEQ over root 2 s squared. I should just say 2s squared, right? I hat plus j hat. Just factored out of both of those. And now these combine into 0.353 KEQ over s squared I hat plus j hat. And I can factor that back in if I want to, but I don't really have to, so that's fine. Okay, so that's EC. Now EH is going to be very, very similar. So in fact, it's going to be, because of the geometry, we know it's going to be exactly the same. It's just that these vectors are going to be different. So h is going to affect it doesn't add anything to the y value. It only adds to the x and the z value. So EH, I know right away, is going to be 353 KEQ over S squared. I said it was going to add in for H, it's going to add in the X direction and the Z direction. That's going to be I hat plus K hat, plus K hat. So we have here, let's see if that's right. I hat plus K hat for, they named it something different. H. Yeah, I think they called this one F. They called this one H. That's the only difference. And then now, so that was for F, I should be clear. That was for F. And now for H. EH is again going to be 0.353 KEQ over S squared. And now it's going to be from this position, and that's not going to affect in the X direction. It's only going to affect in the Y, J hat, and K hat direction. And there we go. Those are those three. So now we know the electric field from B, D, E, C, H, and F. So we know B, D, E, C, H, and F. The only electric field we don't know is from G. Okay, so now we have to figure out all the components of the things from G. So it's going to have, we have to figure out its radius, first of all, right? We're going to have to figure out its radius. So the radius from here to here, from there to there, we're going to have to do a little bit of funny business, I think, here. So this angle with this plane is 45 degrees, right? So if we can try to figure out what this length is here, then we can figure out that length because we know the angle and a length. So what that bottom length is it's just going to be root 2s. Root 2s. Right? That bottom length there. So the hypotenuse is going to be root 2s cosine 45 equals root 2s over the hypotenuse, the length we look for, r right there. So root 2s over root 2 over 2, right, because cosine 45 is, sorry, I should be clear, that's that now. R equals root 2 over 2. So we're left with this. Those will cancel. So I'm just left with 2s. Let's see if that is right here. That isn't the radius they used, surprisingly. And I don't understand where they get the radius that they used.
What's the radius they got?
Root 3s.
What if we do Pythagorean theorem? Probably that's not 45 degrees.
But doesn't it have to be? It's a square.
Yeah, this is square, but we're dealing with that diagonal doesn't necessarily be like 45 because the plane is different. I guess it's long in one side and in the height is the height is different from the width, so it's not a complete square.
The height and the width.
Oh wait, yeah, you get root 2s squared, which is 2s squared plus s squared, which is 3s squared. Square root of 3s squared would be root 3s.
Okay, it sounds like you got the answer. What did you do? What?
So,
Pythagorean
whoever said Pythagorean theorem. So we know the side length, like
so
for the triangle that's sort of like in the middle.
This one.
Here. It doesn't make it. I mean, I don't know. I mean, the vertical one, but I don't know if it makes a difference anyway.
Okay, yeah.
Because we're looking for the vertical distance, or not vertical distance, the distance between G and point A.
Yeah.
So then you got 2 root 2 is your base. You have not root 2. You have root 2s is your base. You have s is your height. And then you square both and take the square root after adding them. You get 3s squared.
Yeah. 2s squared plus s squared in the square root, which is going to be root 3s. Okay, so we got that radius. Why did I get a different radius before? I just made a mistake, probably? I guess, I don't know.
It was because of the angle.
Oh, I assumed it was 45, yeah.
GE, yeah, the GE is longer than QQ, like EA.
Yeah,
So
I see. Okay. So root 3s is the radius there. So now I know that at least the magnitude of it, EG is going to be KEQ over root 3s squared. Okay, now I got to figure out all these components. So the components are I don't at all understand the components they use. So let's try to figure it out together. So what they say is that the x component let me see this for a second. Yeah. They say that let's just start with like I hat. So it's the magnitude of EG times cosine theta sine phi I hat.
I think they are going from the floor, like from the XY plane, up, right? So I think the phi angle that they're defining is the one that is between GA and GE. So that's one angle, and the other angle is GHGE. So those are the two
Which
angles.
Is 45. GHGE is
exactly.
45,
Yes.
right?
So they just say, okay, this is the first one, and like this is the first angle, and then we like that angle multiplied by the other angle, and you get the direction.
Okay. So if I try to draw it out here, let's say we're trying to find the x component, which is in this direction. The x component would say, okay, well, I need to find. So it would be, I have a vector like this coming out. That's like the direction of the vector. So I'm going to do this angle here. I'm going to do cosine of that angle there to get it. Yeah, to get it on this plane. Yeah, cosine of this angle, I'm going to call that phi. So it's hard to draw because that's coming 3D out of the screen towards us here, right? So that angle, I'll do it in a better color probably. That'll probably help. So coming out of the screen like that. All right. Actually, I'll make those parallel. So yeah. So there's an angle phi right there. And we'll figure out what that angle is in a second. It's the same direction as that. It's the same as that angle right there. And so now I'm going to take this angle, that magnitude, times cosine of phi, times cosine of, I'll call that phi. I'll call the other one theta. So, and then from that, I'm going to do I'm going to take cosine of 45. Yeah, because then this angle is 45. Right, I'll call that theta, but we know that angle is 45. Right, so then cosine of that would get me on the x-axis. So I'm going to kind of going like there, down onto the xy plane, to the side onto the x-axis. So cosine phi, cosine theta. We know theta. Oh, sorry, why is it sine? Hold on, sine is. That's the x. It doesn't matter actually, because sine and cos 45 are the same thing. Yeah, it doesn't matter. It's just my perspective on this is like different than the solution manual, but that doesn't change the answer. Cosine and sine 45 are the same thing, so I can switch that to a cosine. That's fine. So cosine phi, cosine theta, I hat. Similarly, it's going to be, to get it on the y-axis, it's going to be cosine phi sine theta. So this is I hat plus magnitude of EG cosine phi sine theta. That's theta, not phi. That's j hat. And then to get it on the z-axis, we do EG cosine phi.
It actually is going to be just sine of phi, because that's the reflection on the z-axis. Yeah.
Yeah, that makes sense to me. Yeah, sine of phi. Sine of phi, right? Because we want to get this component like that. Very messy drawing now, I know, but it's what had to happen. So there we go. Now, what are all these values? Theta is 45. Phi we can find not too bad. So phi is this angle in that little triangle inside there, right? This triangle inside there. What are the side lengths of that triangle? I'm going to look from the side here. The base is root 2s. The side length here is s. This is the angle we're looking for, phi. Well, I can just say that phi equals tan inverse of s over root 2s, which is going to be tan inverse of 1 over root 2, which is... Don't open my calculator. Oh, right here. Tan inverse of 1 over root 2 is 35 degrees, approximately. So theta equals 35 degrees. Okay, so 35 degrees is, not theta, sorry, phi is 35 degrees. 35 degrees. So now we essentially have everything we need. I can separate this final EG into a bunch, like into an actual vector, because this is in the k hat direction. So I can say that the actual vector is, well, it's going to be KEQ over root 3s squared times, well, cosine theta. So there's a, oh no, there's no cosine theta at the end there. Hold on. Sine 45. Yeah, there is a cosine. Wait a second, what? Cosine, sine phi? Sine 45. No, that doesn't make sense what they just did. Something in the solution doesn't make sense. They subbed in a number wrong. They did cosine, they did sine theta here. But there's no way that that's sine theta. Because sine theta would give you nothing. Well, sine, nothing. Sine theta would give you nothing. Because it's not, you didn't do a cosine theta first. Or no, sine theta. Yeah, there's not a theta. There's no theta there. So it has to be a sine phi. But then the numbers don't work exactly how they're expecting it to work here. Unless they are. Sine 35 is that. Yeah, the problem is that there's nothing nice to factor out now. That's the problem. So I could switch this to a... Whatever, I could switch this to a sine if I wanted to, and I could factor out sine from this. Okay, then this is the best we're going to get. This is as simple as we're going to get it. So I'll just write it out here. Is KEQ root 3... I guess I could factor that out. That's all I can factor out. So there you go. I'll just do it like this. Cosine 35 sine 45 I hat plus cosine 35 sine, you know what, I'll make this a cosine again just to avoid a little bit of confusion if people are reading this after. Sine 45, just remember sine and cosine 45 are the same thing. And this is just sine 35. This was j hat and this was k hat. So, someone's got their mic on. Everybody check their mics. So, from here, we will just do, this is our EG. So now to figure out the net electric field, we just add all the vectors we just got. So let me just highlight all of them. These are all vectors that we have to add together. This is a vector. These three. So we have 6. These are 3 up here. And then finally this one we have to add to that. The sum of all these vectors is, E total is the electric field at that point, right? So we're going to have to add them together. So KEQ, so let's add all the J hats together first, I guess. Or all the I hats. I don't know why J hat first. It's I hat first. So let's start from here. Abdul, you got your mic on. Okay, thank you. So KEQ over root 3s squared. Well, let's figure out what, well, whatever. Cosine 35 cosine 45 I hat. So this is just the I hat. Plus. Plus. Let's see. Next I hat I have is this one, KEQ over S squared. KEQ over S squared. Okay. Then we have this I hat here. There's no more I hats up there. No more I hats here. So 0.353 KEQ over S squared. KEQ over S squared. And that's it for here. Okay, then 0.35. So times 2. I have another one. So times 2. And that's it. And that's it from here. That's our I hat. That's our I hat. Now our, sorry, not equals, plus our J hat. So J hat is KEQ over S squared. Start there. KEQ over S squared. Okay, next one is 0.353 KEQ over S squared. KEQ over S squared. Times 2, because I have another one from here, or another one from here, so times 2. And then finally I have my J hat from down here, so it's going to be plus KEQ over root, wait a second. Yeah, makes sense, never mind. Over root 3, what was it? Root 3s squared. Cosine 35 sine 45. Yeah. Plus, that's it. Never mind. That's our J hat. And finally, our K hat is going to be KEQ over S squared. They always have that in it. KEQ over S squared. Then our K hat from here is going to be 0.353 KEQ over S squared, and 2 of them. 3 KEQ over S squared times 2, because I have another one from here. And then finally, the K hat here is finally just sine 35, and that is our K hat. And that is the field, the electric field at that point. So that's the field. I can simplify, of course, but that's fine.
Aren't all 3 components supposed to be equal?
The forces are supposed to be equal. You're right. Yeah.
Which would mean that the fields would have to be equal as well.
That's true.
They might be equal, actually.
Let's see.
We haven't calculated it, but
Well,
they don't.
They all have
calculated
this.
first.
The only thing that's screwing me up is... What happened? This sine 35. That's what makes everything not quite right. So look here. All the components have a KEQ over S squared. That's fine. They also all have a cosine 35 sine 35. Well, almost all of them. It's just that, sorry, cosine 35, yeah, sine or cosine 45 doesn't matter because sine and cosine of 45 are the same thing. Except down here, for some reason, it's a sine 35. The components aren't the same, even in here.
I feel like Slater just did not solve this one correct either.
No, I don't think so either.
I don't know how these can all be the same in a cube.
Yeah. I don't know either. I don't know how either, because this, right, they definitely made a mistake here, because they said 45. They said to use theta here, which is not true. Right? So theta is... Here I had cosine 35, cosine 45. Yeah, so that's definitely not right.
The answer for sine 35 and cosine 35 times sine 45, they are roughly the same. It is 0.579 and 57.3, so it's not big of a difference.
So it was just put in the numbers and it should come out the same.
Cosine 35, cosine 45. I'll just say that divided by sine 40. No, messed up.
Sine 35.
That divided by sine 35?
Yep.
35.
Yep.
Yeah, they're approximately equal. You're right.
Yep.
So what we can do, yeah, you're right. So these are all equal because, oh, I messed up. Sorry, I missed a thing here. This is KEQ over root 3s squared sine 35. So they are all equal because look, this is equal to this and this. This is equal to this and this. And this is equal to this and this. So they are all equal. All the components are equal. Hopefully that makes sense. So now that we know that, this is right. This is fine. So we have this. This can simplify. It can simplify. And how about I just, well, yeah, you know what? All these coefficients are equal here. So we could factor it out, of course. We could factor it out. So it would be it would be KEQ over S squared plus 0. I'll just say 6. That's too complicated. 0.353 times 2 is 706. KEQ over S squared plus, okay, well, what's root, what's sine 35 over 3 is what I'm looking for. Sine 35 over 3. Sine 35 divided by 3 is 0.19119 KEQ over S squared times I hat plus J hat plus K hat. That's fine. So from here, we can just factor out the... What? How is that less than 1? Oh, no.
Which question is this? Which number
48.
question is this?
48.
48. Okay.
22. So then we can factor this out into 1 plus 0.706 plus 0.19119 KEQ over S squared. I hat plus J hat plus K hat. And hopefully this plus 1 plus 0.706 is 1.9 KEQ over S squared. I hat plus J hat plus K hat, which, like we said an hour ago, 1.9 is the value that we should have there in front of the coefficient. So
you're telling me the root 2 magic that I found out was completely a coincidence? Damn.
Well, these numbers come from some kind of root 2, so who knows? I don't know. I didn't keep track of the root 2s. We just pushed the decimals. But yeah, probably just magic. Probably just some magic that happened there. Okay, we have the electric field. This is the electric field. E field. Now, to find the force, not too bad, just QE. So F equals QE. So that's going to be 1.9 KEQ squared over S squared. I hat plus J hat plus K hat. There we go. That's the force. Now to find the other parts of the question, which are not very long, so they'll be fine. What is the magnitude and direction? So magnitude is not hard to find. Magnitude is just going to be... why did they give us... Yeah, here, magnitude's here. To find the magnitude, what we just do, since all the components are the same, right, it's just going to be the square root of... So the magnitude of the electric field is going to be the square root of 3 times any of the force components. So say Fx squared. Does that make sense? In other words, it's going to be root 3 times root 3. Well, you know what? I'll leave that on the screen. Okay, I wrote that. So that's going to be root 3 times fx or fy or fz. Doesn't matter. They're all the same. So root 3 times that. So then we just do root 3 times that. And so the magnitude is going to be any one of the force components. So it's going to be root 3 times 1.9 times keq squared over s squared. So root 3 times 1.9 is 3.29. So you can just call this 3.29 keq squared over s squared. That is the magnitude of the force. Sorry, not the electric field. The force. And then finally,
It's not necessary to put the. It is the q square or q.
Q square. It's q squared because it's a force. So you multiply by q.
Oh, okay, yeah, got it. So right. the electric field is just 1q. Okay, I got it.
The electric field is just 1q, but the force is q squared.
Yep.
Here's q. And now finally we need the directions. So to find the direction, we just need to find, for some reason they only give 2 components. I don't know, whatever, it doesn't really matter. Okay, I don't really know what they're saying here. I don't really know what they're saying here, but essentially, if we go up to the picture here, we know all the components, so we just want to find the coordinate direction angles, I guess, for it. So the coordinate direction angles, if I remember correctly, or is that what we need to find? What is it that we need to find here? They're saying the azimuthal angle of the, the azimuthal angle of the is given by, so there's a lot of typos in here, and the polar angle theta is given by.
Do they just find alpha, beta, gamma, like the 3 angles to each what do you call it, thing, each direction?
That's not what they did, but that's what I would do here. The direction of the total force. Yeah, that's what I would do.
Or do we just give them phi?
No, you know
the
what?
Direction.
I think what we need to do, since we're in 3D. Yeah, go for it.
The direction is going to be the same as the electric field, isn't it?
Yeah, it is. We just need an angle. We need a specific. We need an actual number, right?
Oh, right. But we already have the 2 angles here, theta and phi. So
and those are the angles that they use in their answer. So what I'm quite certain is that they're using this azimuthal thing. Let me look up what that is. Yeah. So what that is essentially you give the angle on the xy plane from the x-axis, and then you give the angle up in the z direction. And that's the azimuthal direction angles of this. So that's what they do in the solution. In the Slater solution. They say the azimuthal angle is theta equals 35. Oh, no, sorry, theta equals 45. That's the angle from the x-axis to the y-axis. And then phi is 35 degrees, which is the angle from the xy plane to the z-axis. And that's 35, so that's going to be phi, and that's going to be theta. So that's the angles. That's the direction that it goes in. And yeah, there you go. So that took quite a while, but we finished it. We finished chapter 22 at least. So hopefully tomorrow after the CPS exam, we can get some stuff done. Definitely at least get chapter 23 done. No, we gotta get a move on. I'm gonna be honest. We gotta get a move on. So definitely chapter 23 done. I thought we would have enough time to finish all these questions, but it might not seem like it. We didn't get too much done. We'll see how much we get done tomorrow, and then if we're really struggling to finish everything, then I'll just choose some questions for the 3rd day if we're really struggling. So for tomorrow, we'll still just keep going in order, and we'll see how much we get through.
How many chapters do we have left? 23
1, 2, 3,
28?
4, 5. Chapter 23, 24, 26, 28, and 29.
Okay.
So quite a bit. Quite a bit. 29 is sources. Oh yeah, 29 is like what's it called? The Biot-Savart law. And yeah. So we do have quite a bit left. So, you know, again, like I said, we're going to just continue question by question tomorrow. Maybe we'll see if we might skip a few. Maybe I'll skip some more that are like not worth the time to do. And I'll decide that, and maybe we'll decide it together. And then if we're really behind by the end of tomorrow, then I'll just choose questions to do for the third day instead of going through them one by one. But yeah, that is everything for today. That's the whole thing. I just realized my shirt is sideways. So hopefully, you know, this was helpful. I've been going for 4 hours, 3 hours and 51 minutes. So there we go. I mean, of course we took a break. Actually, 2 breaks, which is good. So yeah, then that's everything for today. I'm here for a few more minutes if anybody has any more questions. Otherwise, hope to see you guys tomorrow at noon for CPS, or tomorrow at 6 for PCS, and the day after at 5 PCS.
What time tomorrow for CPS?
CPS is at noon.
At noon. All right. Just want to say thank you. This one was really helpful.
No
This last
problem.
one.
I'm happy it was.
Whoa, wait. I have an important question.
Okay.
What happened to the glasses?
That's true. I didn't put them back. I didn't put them back on. I guess they worked. I don't have a headache anymore. So
Your coolness factor went down.
That's true.
Like,
That's true. That's true. I'll make sure I have them on for next time. Okay. Well, yeah, I'm just here for another minute. Any last questions? Anybody can ask me anything? But yeah, if otherwise, have a good night. Get some
Do
sleep.
you know what you're doing tomorrow for PCS?
For PCS, we're gonna start chapter 23. We're gonna do chapter 23. Definitely make it all the way through chapter 23. I very much hope so. We get to chapter 24. And actually, I really hope we get a significant way through chapter 24. Chapter 23 only has 5 questions, so 24. Yeah, I hope we get 1, 2, 3, 4, 5, 6, 7, 8, 9. How many did we do today? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the last, I'd say that last question is like counts for 3 questions. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I think we could get through chapter 23 and chapter 24 tomorrow. It's possible. If I skip a few questions, maybe, and skip parts that are not worth the time, I'd say tomorrow we're going to do chapter 23 and chapter 24.
Netflix isn't quite as bad as like the electric fields and stuff, just because it's the what's it called? What's that rule called? The cross product rule or whatever makes it a little easier. Just oh no, that's not cross product. That's dot product for Netflix. Cross product goes into magnetism.
Oh yeah.
Dot product it's the dot product with the area and the flux.
Exactly. So yeah, we will go through that tomorrow. But yeah, there you go. Thank you for Andrew who's streaming. Thank you for streaming.
Yeah, no worries, bro.
See you. And yeah, so I'm just here for another 2 minutes. Anybody has any questions? Otherwise, have a good night. I will stop recording and upload this right away.